Picture a piece of frozen ground high in the Transantarctic Mountains, a few hundred miles from the South Pole. A slab of old glacial till, grey and gritty, splits open along a hidden seam. Inside it lies a twig. Just a twig, barely over an inch long, no thicker than a pencil. Under a hand lens it gives up its secret slowly. More than 60 growth rings, crowded into a stem about 1 1/3 centimetres across, roughly half an inch of wood. 60 years of life held in something you could tuck behind your ear. That fragment came out of a place called Oliver Bluffs in the Dominion Range, from a body of rock known as the Sirius Group. It is a piece of southern beech, a tree carrying the careful scientific name Nothofagus beardmorensis, and it is, as far as anyone can yet confirm, a surviving splinter of the last forest Antarctica ever grew. Let the scale of it settle over you. 60 rings in most of the world means a tree with some weight to it. A trunk you might not fit both hands around, a crown throwing real shade. Here, 60 rings meant almost nothing above the ground. This beech never rose higher than the top of a boot. It was mature, finished, as old as a long human life, and still no thicker than the pencil you would use to sketch it. Each ring is a summer. Each summer added a layer thinner than a hair, a plant racing to grow through a few brief warm weeks, then shutting down, waiting, holding, for month after month of cold and dark. You do not need to hold all of this at once. Settle in, get comfortable, let your breathing slow. We have a very long way to travel tonight, and we're going to travel it gently, one fossil and 1 degree of latitude at a time. There is no hurry here. The forests we are about to walk through are all gone, every last leaf of them, so nothing we do can be too late. Because that twig is the end of the tale, not the beginning. To feel why a tree would spend 6 decades growing no taller than your ankle, you have to understand that Antarctica was not always this white silence at the bottom of the world. For most of the time there has been complex life on land. The South Polar region was green. Not lush everywhere, not always, but forested in some form across a stretch of time so long it is hard to make the mind hold it. Consider the number. Antarctica carried forest cover in one shape or another, from at least the Permian through the Eocene. That is a span of more than 200 million years. 200 million. Long enough that the trees changed their entire body plan more than once. Long enough that whole families of plants evolved, spread, and vanished while the continent stayed wooded. And here is the part that unsettles the tidy picture in your head. For tens of millions of those years, Antarctica was not drifting toward the pole. It was already there. A forested land sitting over or very near the bottom of the Earth, turning through the strange polar rhythm of light. To see how that was even possible, you have to unlearn the map you carry. Forget the lonely continent ringed by cold ocean. For most of this history, Antarctica was not alone at all. It sat at the heart of a single vast southern landmass called Gondwana. South America, Africa, India, Australia, and Antarctica were joined into one enormous body of land, and Antarctica lay near its centre, sutured to its neighbours along coastlines that no longer exist. You could have walked, in theory, from the ground beneath modern Argentina, across what is now Antarctica, and on toward Australia, without ever meeting the sea. That connection mattered more than almost anything else in this history. A joined continent shares its plants and animals freely. Seeds drifted, spores blew, root and branch and beetle spread across the whole southern world. So the forests that grew on Antarctica were not some isolated experiment. They were part of a single great southern woodland, the same broad community of ferns and conifers and later flowering trees that clothed the lands all around it. When you picture Antarctic forest, picture it as one panel in a canopy that stretched across half a hemisphere, and that whole southern canopy sat under a warmer sky. For long stretches of the Mesozoic and the early part of the age that followed, the Earth simply held more heat. The air carried far more carbon dioxide than it does now. There were no great polar ice caps anchoring the cold. Warm ocean currents still flowed freely toward the south, unblocked, spilling their heat onto the polar coasts. Under that kind of sky, a pole could be cold and dark for half the year and still never freeze hard enough to kill a forest. The trees did not need the sun to be high. They needed only for the winter never to bite all the way to the root. That is the world you have to stand inside to understand any of what follows. A pole with no permanent ice, a continent joined to its neighbours sharing their green, a sky thick enough with warmth to let broad leaves unfurl within sight of the bottom of the planet. It is so far from the Antarctica of today that it can feel like a different planet entirely. It was the same ground, the same rock beneath your feet, only the world above it has changed. Now let us put a real forest on that ground, and a real place, and a real latitude, so this stops being an abstraction and becomes a wood you could walk through. Travel back into the early Cretaceous, well over 100 million years ago, to a piece of the Antarctic peninsula that geologists call Alexander Island. Today it is a frozen shelf of rock and ice along the peninsula's western flank. Back then it held a living forest, and we know almost exactly how far south that forest stood. The reconstruction places it at a paleo-latitude of roughly 71 to 72 degrees south. Sit with that figure for a moment. 71 degrees south is not the edge of the polar world, it is deep inside it. It is a latitude that today would put you out on the ice, well south of the Antarctic Circle, in a place where the sun vanishes for months. And there, at that latitude, in that darkness, stood a forest whose productivity, as far as the fossil wood can tell us, was comparable to temperate forests growing in mild parts of the world today. Think about what that means for the trees themselves. A temperate forest today expects a normal year, a sun that rises and sets, a spring that eases in, a growing season measured in a steady rhythm of days. The Alexander Island forest got no such thing. It got months of unbroken summer daylight, the sun wheeling around the sky without ever going down, and then months of winter when the sun never rose at all. Not dim, not short days, gone. And still those trees grew as vigorously as woods in far gentler places. They found a way to pack a full year of living into the half of the year when there was light to live by. We are not guessing at that rhythm. The trees wrote it down in their own wood, and we can still read it. When you cut across a fossil trunk from these polar forests and look closely at the rings, you see something a forester from the temperate world would find strange. Each ring is dominated by wide bands of what is called early wood. Early wood is the pale, open, fast-grown wood a tree lays down when conditions are good, and it is racing to build tissue. And then, where you would expect the dense dark band of late wood that marks a tree slowing down toward autumn, there is almost nothing. Very few late wood cells. The ring simply runs wide and pale and then stops. Read that pattern slowly because it is the whole secret of these forests in a single image. In most modern high-latitude woods, what limits a tree is temperature or water, the cold or the drought that shuts growth down gradually. The tree tapers off, laying denser and denser wood as the season fails. But the Antarctic trees do not taper. They grow flat out, wide and pale, and then they simply switch off, all at once. That abrupt stop is the fingerprint of light, not cold. These trees were limited chiefly by the coming of the dark. When the sun went, growth ended, not slowly but like a snuffed candle. When the sun returned, growth resumed at full pace. The rings record the swing of the polar year more clearly than they record anything else. So the wood tells you the light was the master here. 6 months, more or less, of daylight that never fully quit, when a leaf could photosynthesize around the clock, gathering energy at midnight as readily as at noon. Then the long turn into darkness, when the whole forest went quiet and still and waited. It is a rhythm no living forest fully shares, because no forest today grows at 70 degrees south in a warm world. The nearest thing we have is the far north, but even there the cold usually intervenes before the dark can. In Cretaceous Antarctica, warmth was cheap and light was precious. the trees budgeted accordingly. Try for a moment to stand inside that summer. The light is strange and level, coming in low from all around the horizon as the sun circles rather than climbs. It does not beat down. It leans in, sideways, gold and constant, and it never leaves. There is no evening. Under that ceaseless light the canopy works without rest. Ferns unrolling in the understory, conifer needles drinking the endless day. It is warm enough, wet enough, alive in a way that the white plateau of today gives no hint of. And every green thing in it is quietly aware, in the language of hormones and stored sugars, that the dark is coming and there is only so much time. Then picture the other half of the year, the half the trees spent in shutdown. The sun slips below the rim of the world and does not come back. The forest stands in a dimness that deepens to true dark, week after week. Nothing grows. The deciduous trees have long since dropped their leaves and stand bare. The evergreens hold their needles and simply idle. Snow may sift down through the still air and settle in the branches. And the forest waits, not dying, only paused, holding its life folded up inside bark and root and bud until the first thin return of the light unlocks it again. That waiting, that annual holding of breath, is the discipline every Antarctic forest lived by for 200 million years. Now, here is a gentle place to pause and let you know what kind of journey you have joined tonight so you can let go into it. This is the slow tale of how that green pole died. Not in a single catastrophe, not in one bad winter, but across an enormous span of time, degree by degree, ring by narrowing ring. If you are drifting in and out, that is exactly right. You can follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice, and let the rest of this wash over you as you fall asleep. Nothing ahead requires your effort. It only asks that you rest and let the forest thin around you as we go. Because thin they will, and it helps to know the shape of the descent before we walk down into it, the way you might glance at a long staircase before starting down in the dark. Keep in your mind 3 pictures. Hold them loosely. We will arrive at each one in its turn. The first picture is the high point. Tall, wet, temperate rainforest, growing within a few degrees of the pole. Real trees with real trunks, a closed canopy dripping with moss, a floor of ferns and fallen broad leaves, rain measured in feet per year. A forest you could get genuinely lost in. That is where Antarctica's green story reaches its fullest, warmest expression, long after the dinosaurs are gone, in the age of early mammals and birds. A pole clothed in something close to the mild rainforests that survive today in southern Chile and New Zealand. The second picture is the long thinning. As the world cools and Antarctica pulls away from its neighbours and seals itself inside a cold ring of ocean, that tall rainforest cannot hold. It does not vanish overnight. It shrinks. The canopy drops. The trees that once stood upright begin to crouch. Rainforest gives way to a patchwork of dwarfed woodland and open tundra. Low conifers and stunted beech bent close to the ground. A landscape more like the ragged tree line of a cold mountain than a forest proper. The green does not leave all at once. It gets smaller and lower and tougher and rarer over millions of years. And the third picture is where we began. The final huddle. A few last beeches, no taller than your boot, growing so slowly that 60 summers built a stem the width of a pencil, clinging to bare ground in brief cold summers a few hundred miles from the pole. The ground-hugging remnant of a forest that once towered. After that, the ice. Not the seasonal snow the old forests had always known and always survived, but permanent ice, sheets of it, closing over the whole continent and holding it shut. The green light goes out, and the white silence you know from every photograph settles in and stays. That is the arc. Rainforest to dwarf scrub to a final ankle-high huddle, and then ice over everything. Tonight we are only at the top of the staircase, in the deep past, learning how a forest could live at the pole at all. In the passes to come we will walk all the way down it, into the warm Eocene peak, through the great cooling that sealed the continent off, into the last tundra and the last contested beaches, and finally into the ice that ended it. But we stay, for now, up here in the long green age, where the trees still stood tall, and the pole still turned green and dark and green again, year upon year for longer than the mind can really hold. It is worth dwelling on that endurance, because it is the true marvel, more than any single tree. 200 million years of forest is not a streak of good luck. It is a plant lineage solving the same brutal problem, the vanishing of the sun, over and over, across changing worlds. The conifers of the Permian solved it. The strange seed ferns and cycad relatives of the Triassic and Jurassic solved it. The first flowering trees arriving in the Cretaceous solved it too, and the southern beeches after them. Each in their own way learned the polar discipline. Grow hard in the light. Wait through the dark. Drop your leaves or hold them, but above all do not die in the waiting. And they had help from the shape of the world, right up until the world changed its shape. Gondwana kept Antarctica connected, so fresh green kept arriving. The warm currents kept the coast from freezing. The thick carbon-rich air kept a floor under the temperature, so the winters, however dark, stayed survivable. Every one of those supports would eventually be pulled away, one by one, and when they were, the forest would follow them down. But not yet. For now the supports hold, the pole stays green, and the trees keep their 200 million year vigil over the bottom of the earth. Fix that image before we go on. A polar continent, joined to half a world, wearing a forest. Summers of endless slanting gold when the canopy works without rest. Winters of total dark when it stands and waits. Rings of wide, pale wood that stop dead where the light stops, then start again where the light returns. A green pole, patient, ancient, and for all its strangeness, thoroughly alive. That is the world we're leaving the ice out of for as long as we possibly can. We began tonight with the ending, with that pencil-thin twig and its 60 crowded rings, a tree that lived a human lifetime and never cleared the top of a boot. Everything from here is the long approach to that small, stubborn survivor, the tracing of a forest from its full height down to its final crouch. To understand how a forest came to hug the ground like that, you first have to stand inside the tall, wet rainforest that once grew almost at the pole. To understand how a forest came to hug the ground like that, you first have to stand inside the tall, wet rainforest that once grew almost at the pole. So let the cold present fall away, and set your feet down instead on soft, dark ground near the tip of the Antarctic Peninsula. The place is Seymour Island, though no such name exists yet. It is the early Eocene, somewhere between 50 and 40 million years ago. You're standing at paleolatitude near 65 degrees south, a few degrees from the bottom of the world, and there is a rainforest closing over your head. Look up first. The canopy is a broadleaf and conifer roof, layered and dripping. Broad leaves spread out flat to catch the low light. Between and above them rise conifers, tall and dark and needled, holding the highest tiers of the forest. The air is cool but not harsh. It is wet, heavy with the smell of moss and leaf rot, the smell of a forest that never truly dries out. This is not the bare, wind-scoured rock of Antarctica as you know it. This is living ground, deep in litter, breathing slowly around you. Feel the temperature on your skin. The mean annual temperature here, as scientists reconstruct it from the fossil leaves, sits at about 10.8 degrees Celsius. In the units you carry to sleep, that is close to 51 degrees Fahrenheit. Give or take a little under 2 degrees of estimating error. That is not tropical warmth. It is the mild, damp coolness of a maritime forest, the kind of air that beads on leaves and never quite lets them go dry. And that number comes with its own honesty built in. It is a best estimate drawn from the shapes of leaves, not a thermometer reading carried across 50 million years, so hold it gently as the careful figure it is. Now feel the rain. Roughly 60 inches fall here in a year. That is 5 feet of water measured against a wall, arriving not all at once but through a long, markedly seasonal wet climate. There are wetter stretches and drier stretches across the year, a rhythm the leaves record in their form. 60 inches of annual rain is what keeps this canopy soaked, what feeds the ferns underfoot, what hangs the moss in wet ropes from the branches. You're standing inside a temperate rainforest, and it is raining, or it has just rained, or it is about to. None of this is guessed from nothing. This is one of the best read fossil forests on the whole continent. Paleobotanists working this single hillside have pulled more than 1,600 fossil leaves out of the rock. 1,600 separate leaves, each one a flattened impression pressed into stone, each one lifted out and sorted and studied. They come from several named fossil plant assemblages layered through the deposit. There is one called Flora too. There is the Weeman Flora. There is an assemblage called Kukulea Wai. Together they span from the late early Eocene into the early late Eocene, a long window of forest life caught in stacked layers of rock. Think about what that work actually looks like, because it grounds everything you're standing inside. Someone kneels on cold Antarctic ground, in a place that is now bare and frozen, and splits the rock along its bedding planes. The stone opens like a book. And there, on the fresh surface, is the dark outline of a leaf that fell 50 million years ago. Its edges are visible, its veins are visible, its shape can be measured. Do that 1,600 times across 4 assemblages, over decades of returning field seasons, and you build a forest back up leaf by leaf. The leaves themselves carry the climate in their outlines. Many of them are tooth-edged, their margins lined with small serrations rather than running smooth. That detail matters more than it looks. Across the flowering plants, the proportion of leaves with toothed margins tracks with temperature, and forests in cooler, wetter places tend to carry more toothed leaves than forests in the heat. So when researchers measure the margins across a whole assemblage, the leaves themselves point toward a cool, wet, temperate setting. The stone is doing the reading. The forest wrote its own weather report into the shape of its foliage, and when they look for a living forest to compare this to, they find the closest matches scattered around the modern southern hemisphere. The leaf assemblages here read as comparable to the cool temperate rainforests of southern Chile today. They read like the forests of New Zealand. They read like the wet woodlands of Tasmania. Older layers still, from the Paleocene Cross Valley flora nearby, are used the same way, as cool temperate rainforest analogues from an even earlier chapter of this same long forest. So if you want to feel what it was like to stand where you are standing, you can almost do it in the present. You can walk into a Valdivian forest in southern Chile, into the moss and the dripping podocarps, and something close to this Eocene air is around you still. Stay with that engagement for a moment, because it is worth knowing what you are actually resting inside. This is not a painting invented for a calm voice to describe. Every layer of this forest is anchored to counted leaves, measured margins, and named rock. The comfort here is real. You're lying down inside a place that genuinely existed, reconstructed by patient hands, and you can trust the ground under you even as you drift. Now bring your eyes back down from the canopy to the great dark columns holding it up. The backbone of this forest is conifer, and specifically the podocarps. The fossil wood tells this part directly. When researchers study the petrified wood from this formation, the most common type they find is a wood called Phyllocleidoxylon antarcticum. Alongside it are other conifer wood types, ones called Cupressinoxylon and Agathoxylon. Read together, the wood points to a forest whose canopy structure was carried by the podocarp conifers, an ancient southern family of trees. That family is not gone. Podocarps still live in the same southern lands that echo this forest. They grow in New Zealand today. They grow in Chile. They grow in New Caledonia. They are tall, slow, dark-needled trees, and their descendants are still standing on the far side of 50 million years. So when you look up at the conifer crowns holding the highest tier of this Eocene canopy, you are looking at the ancestors of trees a person could walk beneath tonight, in a wet forest at the bottom of the modern world. The wood in the stone and the wood in those living forests belong to the same long line. Rest your hand in your mind on one of those trunks. The bark is wet. The wood beneath it grew in a way no modern temperate tree quite repeats, and the growth rings prove it. When paleobotanists cut and polish fossil wood from these Antarctic forests and look at the rings under a lens, they see wide, pale bands of early wood, the fast spring and summer growth, and almost no dark late wood, the slow, tight, end-of-season growth. That pattern is a fingerprint. It says these trees were limited not by cold and not by lack of water, but by light. They grew hard and fast while the light poured down, then shut almost fully off when it went away. Because that is the strange gift and strange burden of a forest this close to the pole. The sun does not behave here the way it does in the mid-latitudes. For something like half the year, in the deep polar summer, the light never fully leaves. The forest stands in a long, low, circling daylight that does not set, and it photosynthesizes on, hour after hour, week after week. Then the balance tips and the darkness comes in the same way, months of it, a true polar night lying over the canopy. The trees wait it out. The rings in their wood still hold that rhythm, the wide light-fed bands and the narrow dark-starved edges, a clock of the polar year turning inside the trunk. Try to hold both of those seasons at once, because they are the deepest strangeness of this place. You're in a rainforest, mild and green and dripping, and yet for months on end it will lie in unbroken dark. There is no month of killing tropical heat. There is instead a long summer of ceaseless light and a long winter of ceaseless night, and the forest has shaped itself entirely around that swing. The leaves you keep finding in the rock fell through that same alternating light. Some of them dropped in a summer that never went dark. Some of them dropped into the leading edge of a winter that would not see the sun again for months. Let your attention fall now to the forest floor, which is where a sleeping mind likes to settle anyway. Under the canopy and the conifer columns, the ground is soft. It is a floor of ferns and broadleaf litter, layer upon layer of fallen leaves slowly going back into the soil. Ferns spread their fronds in the filtered green light. Broad dead leaves lie tumbled across the moss, the same leaves that, in a few of these places, will one day be split back out of stone by a kneeling researcher. The whole floor is damp. 60 inches of rain a year keeps it that way. Water moves through the litter, beads on the fern fronds, drips from leaf tip to leaf tip in the long polar light. And it is quiet in a particular way. This is the far south, and even at its warm high point the forest is not the shrieking, humming density of the tropics. It is a calmer, cooler green. The rain is the loudest steady thing, that and the wind moving the high conifer crowns. Picture the light too, because the light is the signature of the place. Even in full summer the sun stays low, circling the horizon rather than climbing overhead. So the light comes in sidelong and gold and long-shadowed for hours at a stretch. A rainforest lit like a permanent late afternoon, warmth without a high sun, green under a slanting, circling light that never quite climbs. Let me leave one gentle marker here in the middle of the walk, and then we go straight back into the forest. If this slow travel through deep time is the kind of thing that quiets your mind at night, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. That is all. Settle back into the litter and the rain. It helps to widen the frame and see just how deep in time this forest sits, because the roots of it run back almost unimaginably far. Antarctica carried forest cover, in one form or another, for more than 200 million years. From at least the Permian, through the age of the dinosaurs, and on into the Eocene where you are now standing, this continent wore trees, and it wore them for tens of millions of years after it had already drifted into a near-polar position. This is the crucial thing to hold. The land was near the pole, deep in that punishing light and dark cycle, and still it stayed green. Long before your Eocene rainforest, an early Cretaceous forest grew on what is now Alexander Island, at a paleo-latitude around 71 to 72 degrees south, even closer to the pole than here, and its wood shows productivity comparable to temperate forests today. Forests at the pole were not a fluke. They were the long, ordinary state of this place. So the rainforest around you now is not a beginning, it is a high water mark. It is the warm crown of an enormously long forested age, the point where the trees stood tallest and wettest and most alive before the long descent began. You are standing at the top of a curve that runs back 200 million years and, ahead of you, runs down into cold and dwarfing and ice. Right here, right now, in this dripping Eocene canopy, the forest is close to as good as it will ever be again. That is worth feeling as you rest inside it. This is the summit of the whole long climb, and a summit by its nature looks out over the fall on the other side. The mildness holding this forest up is not guaranteed to last, and even now, at the high point, the conditions that made it possible are the ones beginning to shift. The warmth here depends on the ocean. It depends on warm surface water still able to reach these southern shores, still able to wrap the peninsula in mild, wet maritime air. 60 inches of rain and 51 degrees of warmth this close to the pole are not things the land makes on its own. The sea delivers them, and the sea is about to be rearranged. Because through the middle and later Eocene, the map of the far south is quietly loosening. Antarctica is becoming isolated from the other lands it once joined in the great southern supercontinent. The seaways around it are opening. To one side, the Tasmanian Gateway, the passage between Antarctica and what is now Australia, is progressively widening. To the other, the Drake Passage, the gap between the peninsula you stand on and the tip of South America, is opening too. These are slow tectonic movements, land pulling away from land across millions of years, but their consequence for this forest is total. As those gateways open, they set the stage for a new ring of ocean current to close around the continent, a cold circling current with nothing left to interrupt it. That current does not exist yet in its full force, not while you stand here in the warm Eocene canopy. The deep opening of the Tasmanian Gateway comes later, and the great circumpolar current that will one day wall Antarctica off in cold water is still further off than that. For now, the sea around your forest is still warm enough, still connected enough to the wider ocean, to keep the rain falling and the leaves broad and the podocarps tall, but the machinery of change is already turning offshore. The land is drifting, the gaps are widening, the high point holds, but only for a while. Feel then the fullness of where you are standing at the very top of the long green age. The canopy is broadleaf and conifer, layered and dripping over your head. The podocarps hold the high tiers, ancestors of trees still living in Chile and New Zealand and New Caledonia. The floor is deep in ferns and broadleaf litter, soft and wet under a low circling golden light. 1,600 fossil leaves, tooth-edged and measurable, wait in the rock to tell later scientists exactly this. The air holds at about 51 degrees Fahrenheit. Roughly 60 inches of rain fall through the year in a long seasonal rhythm. And for half the year the whole forest stands in a daylight that will not set, then waits out a darkness that will not lift. This is the warm crown of everything. This is the tall, wet rainforest almost at the pole, the one you had to stand inside to understand all the smaller, lower, colder forests that follow. Hold it a moment longer in the mind before you let it go. The moss on the trunks, the rain in the ferns, the long gold light lying sidelong across a green floor at the bottom of the world, mild and alive and near its peak. You can still find that forest in a way, if you know how to read stone, not as leaves this time, but as wood. On Seymour Island, off the tip of the Antarctic Peninsula, the rock of the La Meseta Formation holds fallen trunks and broken branches that turned entirely to mineral. Groundwater crept into the wood over millions of years and left silica behind, cell by cell, until the tissue hardened into rock without losing its shape. Pick up a piece, and it sits heavy in your palm like any river cobble. Then you look closer. The bark texture is still there under your thumb, ridged the way living bark ridges. The growth rings are still there, fine and countable, pressed into something now hard enough to strike sparks. Paleobotanists have logged these silicified trunks at more than one locality across the peninsula, some as scattered logs, some as stumps still standing where the tree once rooted. A stump rooted in place tells you something a loose log cannot. It tells you the forest grew here, on this exact ground, and did not simply wash in from somewhere warmer. To identify the tree, you go smaller than the eye can manage. A worker cuts a sliver of the fossil wood thinner than paper, thin enough for light to pass through, and lays it under a microscope. The cell walls come into focus, the pits between cells, the pattern of the rays that run across the grain. Every conifer family arranges these features a little differently. The arrangement is a fingerprint, and it survives petrification intact. So even after 50 million years, even after the tree has become quartz, you can still name its family. The most common wood in the La Meseta Formation carries the name Phyllocladoxylon antarcticum. It turns up again and again in the fossil beds, more often than any other kind, which tells you it was not a rarity at the edge of the stand, but a dominant tree of the canopy. It is a podocarp wood, a member of the southern conifer group, and its abundance points to a forest run by podocarps, rather than by the pines and firs you might picture from the northern world. Where you find one dominant wood type repeated through the rock, you're usually looking at the backbone of the forest itself. It does not stand alone. Alongside Phyllocladoxylon, workers have named two more fossil woods from the same beds. One is Cupressinoxylon, a wood with affinities to the cypress side of the conifers. The other is Agathoxylon, a name that points toward the Araucarias, the family of the monkey puzzle and the Cori. Three named woods, three lines of southern conifer, all sharing the same wet slopes within a few degrees of the pole. Together they mark the early to middle Eocene of the Antarctic Peninsula, roughly 50 to 40 million years ago, as a time when conifers held the high canopy over Antarctica. It helps to know that these are not ghosts with no living kin. Podocarpaceae, the family behind that most common wood, is not extinct. You can walk into it today. It still grows in the wet forests of New Zealand, in the cool rainforests of southern Chile, in the ridges of New Caledonia in the South Pacific. The Rimu, the Totara, the Miro, these are podocarps, tall and dark and slow, dripping with moss in a mild rain-fed climate. So when you try to picture the Eocene Antarctic canopy, you do not have to invent it from nothing. You can borrow a real forest that survives on the far side of the Southern Ocean and set it down on Antarctic ground. Stand under that borrowed canopy for a moment. The trees are evergreen, their foliage small and tough and layered. The light filters green and low because for part of the year the sun barely lifts off the horizon. The floor is soft with fallen needles and litter. There is water everywhere, in the air, on the leaves, soaking into the wood that will one day turn to stone. This is the world the fossil trunks came from, and the trunks are the part of it hard enough to reach you across 50 million years unchanged. Wood gives you the trees that were big enough to fall and fossilize. But the forest spoke in another material too, one far smaller and far more widely scattered. Pollen. Every conifer and flowering plant releases it by the countless million, and pollen grains are nearly indestructible, coated in a substance that shrugs off decay for tens of millions of years. They drift on the wind, settle into lakes and seafloor mud, and lock into the sediment as a census of everything that was growing nearby. Count and name the grains in a core of that mud, and you can rebuild a forest that left behind no trunk at all. If you are enjoying this slow walk back through deep time, you can follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Now let us follow the pollen east, away from the peninsula, around to the far side of the frozen continent. Off the coast of East Antarctica lies Pridd's Bay, and beneath its seafloor sits a drilled core of sediment that reached back into the late Eocene. In it, palynologists recovered a pollen community dated to about 35.7 million years ago. What they found was a low-diversity assemblage, only a handful of major players, but each one a name you have now met. There is Nothofagus, the southern beech, the flowering tree that will carry the last of Antarctica's forests all the way to the end. There is Araucariaceae, the Araucarian conifers, the same family the Agathoxylon wood pointed toward. And there is Podocarpaceae again, the podocarps, still present, still holding on this far south and this late. That short list matters. A forest with only a few kinds of tree is a forest under pressure, thinned by cold, not the crowded rainforest of the warmer Eocene. From the pollen and its chemistry, workers estimated the conditions this late Eocene stand endured. Mean annual air temperature sat below 53.6 degrees Fahrenheit. Rainfall ran somewhere between 47 and 98 inches a year, still generous, still enough to keep a forest wet. But the warmth was leaking away. This was cool to cold temperate country, a beech and conifer scrub clinging to the East Antarctic shore, no longer the mild rainforest the peninsula had known a few million years before. Set the two records side by side, and you can feel the tilt. The peninsular wood, 50 to 40 million years back, speaks of podocarps in a temperate rainforest running the canopy. The Prids Bay pollen, closer to 36 million years back, speaks of a shrinking karst, beech and araucaria, and podocarp hanging on in cooler, thinner woods. Same continent, later chapter, and the trend already pointing one way. The forest is not gone, but the list of names is getting shorter, and the thermometer, read through the chemistry of ancient soils and grains, is easing downward degree by degree. There is something quietly moving in how much of this survives. A tree falls in a polar forest 50 million years before anything human. Its wood soaks up mineral water until it becomes quartz, keeping its bark, keeping its rings. 10,000 miles away and millions of years apart, another forest sheds pollen into a bay, and the grains sink and wait in the dark. And both of them, the stone log and the buried grain, hold their identities long enough for someone to lift them out and read the names: Phyllocladoxylon, Cupressinoxylon, Agathoxylon, Nothophagus, Araucariaceae, Podocarpaceae. A roll call of the trees that grew where almost nothing grows now. Run your hand over one of those silicified stumps in your mind, the rings crowded near the outer edge, the bark still gripping the wood. It is heavy, cold, and unmistakably a tree, turned to rock at the bottom of the world, and it is proof, harder than any drawing, that Antarctica once wore a living green skin of conifers and beeches, watered by scores of inches of rain, warmed just enough to keep the sap moving through the long polar dark. That warm, dripping world could not last, because far out in the surrounding ocean the map itself was quietly coming apart. That warm, dripping world could not last, because far out in the surrounding ocean the map itself was quietly coming apart. That warm, dripping world could not last, because far out in the surrounding ocean the map itself was quietly coming apart. You have been standing inside a rainforest at the bottom of the world, and nothing in that forest could feel the change beginning. The change was not in the trees. It was in the water and in the gaps between drifting land, gaps that had been narrow for a very long time and were now beginning to widen. Picture the southern continents as pieces of a single old raft, slowly loosening. Antarctica sat at the centre. Around it the seams were opening. Two of those seams matter most, and you can hold them both in mind at once. To one side lay the Tasmanian Gateway, the stretch of seafloor between Antarctica and what would become Australia. To the other lay the Drake Passage, the gap between the Antarctic Peninsula and the tip of South America. For tens of millions of years these had been shallow or closed. Land, or near land, still bridged the way. Warm surface water could not yet make a full loop around the pole. Then the seams deepened. The deep Tasmanian Gateway is thought to have opened around 33 million years ago, when the seafloor there finally dropped low enough for deep cold water to pour through unobstructed. That single fact reshapes an entire ocean. A gateway that had blocked deep flow became a corridor. Water that had been forced to turn back could now keep going, following the coastline, curling around the continent instead of away from it. The Drake Passage tells a slower, more argued version of the same story. As South America and the Antarctic Peninsula pulled apart, the gap between them widened and deepened over millions of years. Estimates for when it became a true deep-water passage vary, and paleoceanographers still debate the timing. What matters for you tonight is the shape of the outcome. With both gateways open, nothing solid stood in the way of a current that could circle the whole of Antarctica, around and around, without ever touching another shore. That current has a name, and it is the largest ocean current on Earth, the Antarctic Circumpolar Current. It runs clockwise around the continent, driven by the relentless westerly winds of the far south, and it moves more water than all the rivers of the world combined. Its onset is estimated near 30 million years ago, once the Tasmanian gateway had drifted into just the right latitude band, aligning with those westerly winds. The winds pushed, the open water answered, the ring closed. Stay with that image for a moment, because it is the hinge of this whole night. A ring of moving water, cold and wind-driven, wrapping the continent like a closed loop of rope. Before it formed, warm currents from the equator could still reach south and brush the Antarctic coast, carrying a little heat with them. After it formed, that warm water was turned aside. The circumpolar current acted as a barrier made of the motion, deflecting the warm surface water back north before it could arrive. You can feel what that means if you think of a moat. Not a moat of still water, but a moat that flows fast enough to sweep away anything trying to cross it. The heat that had kept the forests alive came from far to the north. Now a moving wall of cold ocean stood between that heat and the land. Antarctica was, in effect, sealed inside its own cold ring, cut off from the warmth of the wider sea. The word scientists use is thermal isolation, and it is a plain description of a plain thing. The continent was left to keep its own temperature, and its own temperature was dropping. A place at the pole, deprived of imported warmth, has only the thin winter sun and the long polar dark to work with. The forests had survived at the pole for tens of millions of years precisely because the ocean and the atmosphere kept smuggling heat down to them. Close that supply, and the arithmetic of survival begins to shift. But the ocean was only half of it. Above the water the air was changing too, and this is the part many researchers now treat as the deeper cause. The amount of carbon dioxide in the atmosphere was falling. Carbon dioxide traps heat. More of it makes a warmer world, and there had been a great deal of it during the warm Eocene, well above the levels you would measure today. Through the long slide toward the Eocene-Oligocene boundary, that number came down. Around 34 million years ago, atmospheric carbon dioxide crossed a threshold near 750 parts per million on its way down. That figure is worth sitting with. It marks a doorway. Above it, the planet could stay largely free of permanent ice, even at the poles. Below it, the balance tips. The world becomes a place where great ice sheets can begin to form and, more importantly, can begin to last through the summers instead of melting away each year. There is a stricter figure too, one tied specifically to a continent-sized ice sheet on Antarctica itself. Modelling work places that threshold nearer 600 parts per million, cross below roughly 600, and the conditions exist for ice to spread across the whole of the continent rather than clinging only to the highest peaks. So you have two doorways, close together in the same slow descent. One opens the possibility of ice. The other opens the possibility of an ice sheet that swallows the land. Now hold the ocean and the air together in the same thought, because they arrived together. The circumpolar current was closing the ring of cold water. The carbon dioxide was thinning the blanket of warm air. Neither alone would have to do all the work. Each made the other more effective. A colder ocean and a thinner greenhouse blanket, acting on the same continent at the same time, near the same window of 34 million years ago. You do not need to imagine a sudden freeze. That is not what the rocks record. What the rocks record is a step a distinct cooling step across the Eocene-Oligocene transition, when the whole climate system shifted from a largely unglaciated world to one that could sustain large Antarctic ice sheets. It was a real turning point in the planet's history, and it happened over a span short enough that geologists mark it clearly in the layers, yet long enough that no single winter did it. And here is the honest part, the part the working scientists insist upon, because the details still matter to them. The exact weighting between these causes is still debated. Most current work treats the fall in carbon dioxide as the primary driver, the thing that set the stage and made the cold possible. The opening of the Southern Ocean gateways and the circumpolar current that followed are usually cast as contributing factors, shaping the timing and the pattern rather than pulling the trigger alone. That is the majority view today. It is not a closed case. So when you hear that the Drake Passage froze Antarctica, or that carbon dioxide alone did it, treat both as too simple. The truthful picture is a system of causes leaning on one another. Falling carbon dioxide as the main slope of the descent, gateway opening and ocean circulation as forces that steepened it and locked it in, even the slow wobble of Earth's orbit playing its part in the timing. Modelers still argue over exactly how much each contributed, and that argument is a sign of science working, not failing. If you have been walking with me through the dark of these polar forests and you want to keep company on this long descent into the ice, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Then let your shoulders drop again and come back to the cold coming ashore. Because while the ocean turned and the air thinned, the land itself began to keep a record, and we can read that record now. In East Antarctica, off a coast called Prids Bay, drill cores have pulled up sediment that was once soil, laid down as the transition unfolded. Locked inside that ancient soil are molecules made by microbes, molecules whose exact shape depended on how warm the ground was and how acidic it was. Scientists call these molecules BRGDGGTs, and they act like a thermometer and a chemistry gauge buried in the mud. What they show at Prids Bay is a clear cooling of the land surface across the transition. Soil temperatures dropped from around 55 degrees Fahrenheit to about 46 degrees Fahrenheit. That is not a killing frost. It is a shift of roughly 9 degrees in the ground itself, the difference between a mild, damp forest floor and a cold one where roots work harder and grow slower. A forest can feel a change like that in every season, in every ring it lays down long before the last tree falls. The same molecules record something else, quieter but telling. The soil grew more alkaline, its pH rising from about 6.0 to about 6.7. On land, that kind of shift often points to drying. Wet, leaf-littered forest soils tend to be more acidic, fed by rain and rot. As a landscape dries, as rainfall pulls back and the ground spends more time cold and firm, the chemistry drifts upward. So the Prids Bay record is really two signals braided together. The ground was getting colder, and it was getting drier. Both are hard on a rainforest. Picture that forest floor changing under its own trees. The heavy rains that had fed 60 inches a year begin to slacken. The spongy, saturated soil stiffens. The mosses that draped every trunk find fewer wet months to swell in. None of it happens in a day. But a broadleaf forest is a machine tuned to warmth and water, and you've just turned both dials down, slowly, and left them there. The trees do not die of shock. They die of arithmetic, generation by generation. There is one more line in the land's record, and it comes from higher up. Mountain glaciation in parts of Antarctica appears to begin in the latest Eocene, roughly 37 to 34 million years ago, before the sharpest cooling step at the boundary itself. Ice was already gathering on the high ground, while forests still held the lowlands. The peaks went white first. Small glaciers formed in the cold air of altitude, in valleys where snow could linger through a summer, and then through a second summer, and then simply stay. Hold those two pictures side by side, because together they tell you exactly where the world stood. Down near the coast, at Prids Bay, a cooling, drying soil still supporting a thinning forest. Up in the mountains, the first true ice, quietly accumulating. The white was coming down from the heights and in from the cold ring of the sea, and the green was being pressed between them. Not erased, pressed, narrowed toward the mildest ground that remained. You could have stood in that latest Eocene landscape and not known you were watching an ending. The trees were still there. Some summers were still soft. The light still swung from months of daylight to months of dark, and the wood still laid down its wide pale early wood in the bright half of the year. A single human lifetime, had there been anyone to live it, would have shown you almost nothing. The change moved slower than a life. It moved at the pace of the land. That is the cruelty and the mercy of it at once. Nothing about this transition was violent in the way a flood or an eruption is violent. There was no single catastrophe to point to. No day the forest died. Instead, there was a long, patient pressure, applied from the ocean, from the air and from the mountains, all at once, all gently, over a span that dwarfs anything a person can feel. Cross a threshold near 750 parts per million. Close a ring of cold water near 30 million years ago. Deepen a gateway near 33 million years ago. Each number is a small thing. Together they remade a continent. It is tempting to call a moment like this a geological instant, and in the deep clock of the earth it very nearly was, a step compressed into a slim band of rock. But live inside it, at the speed of trees, and it is anything but instant. It is thousands of generations of seedlings, each one facing a floor a little colder and a little drier than its parent knew. It is a canopy that thins by inches over lengths of time you cannot picture. The forest did not know it was ending. It only knew each year was a little harder than it needed to be. And this is why it is wrong to imagine Antarctica's forests winking out. They did not vanish like a light switched off. The warm, wet rainforest of the peninsula, the one with 60 inches of rain and a floor of ferns, was simply no longer supportable once the heat supply was cut and the carbon dioxide fell away. What replaced it did not arrive from nowhere. It grew out of the same forest, the hardy edges of it, the species that could bear a colder soil and a drier year. So the tall trees gave way to shorter ones. The most tender broadleaves dropped out first, the ones that needed real warmth, and the conifers and the southern beech that could stand the cold held on longer. The forest did not fall. It shrank. It lowered its own ceiling. Where a cool, temperate rainforest had stood within a few degrees of the pole, a tougher, sparser woodland began to take its place, ready to face a world that would keep asking more of it. None of this was going to reverse. That is the quiet weight of the Eocene-Oligocene transition. Warm spells would come again, some of them long, and forests would rally in them for millions of years more. But the great warmth of the Eocene, the deep planetary heat that had let a rainforest live at the pole, was not going to return in the same measure. The doorways had been crossed. The ring of cold water had closed and would not open. The trend of the whole world had turned toward ice. You can still find in the language of the rocks the exact grammar of that turning. A cooling step in the ocean chemistry, a drop in the land temperature at Pridd's Bay, a rise in soil pH toward dryness, the first mountain glaciers in the latest Eocene, pollen assemblages growing lower in diversity, the delicate types thinning out, and the cold hardy types remaining. Read together, they do not describe a death. They describe a long exhalation, a world letting go of its warmth one measured breath at a time. It would be easy, from here, to say the forests began to fade away and leave it there, as if the story were nearly over. But that would miss what actually happened next, and what actually happened next is the most patient part of all. The green did not leave the continent at the boundary. It changed its shape and dug in. It traded height for endurance, and it kept living at the pole for tens of millions of years after the first ice appeared, in forms you have not met yet tonight. Think of the whole transition, then, not as a wall, but as a slope. On the high, warm end stands the Eocene rainforest of Seymour Island, dripping and dense. At the far, cold end lies a continent of ice, and the transition near 34 million years ago is the place where the slope tilts, where the descent truly begins in earnest. Everything after it happens downhill. The ocean had turned, the air had thinned, the ground had cooled and dried. The map out in the surrounding sea had finished quietly coming apart. But a slope is not a cliff. A tilting world still gives its forests time, and the trees used every year of it. The last thing to grasp about this turning point is how little of it was sudden. The circumpolar current took millions of years to fully assemble. The carbon dioxide fell across a long descent, not a single drop. Even the great step across the boundary, sharp as it looks in the rock, spanned lengths of time no living thing could witness whole. The forest was never asked to survive a single catastrophe. It was asked to survive a slow, unrelenting cooling, and for a remarkably long while it did. That is the note to carry forward into the cold that follows. Not fire, not flood, not a night the trees froze where they stood. Instead, a continent slowly sealed inside its own weather by an ocean current and a thinning sky, and a forest that answered the pressure the only way a forest can, by becoming smaller, tougher, and more sparing of itself, year over slow year. A paleobotanist kneels on a cold slope and sets a chisel against the rock. One tap, then another, and the stone splits along a seam it has held for tens of millions of years. Inside lies a leaf, pressed, flat and dark, no larger than a fingernail. This is where every number you have heard so far begins, not with a thermometer buried in the past, but with a shape in stone, sorted and measured by patient hands. Think about what that leaf actually is. It is a thin carbon film, a compression, the flattened ghost of tissue that fell into mud one autumn and never rotted away. On Seymour Island, off the tip of the Antarctic peninsula, workers have pulled more than 1,600 such leaves from a single set of Eocene hillsides. They come out one at a time. Each is brushed clean, laid in a tray, and turned toward the light so its edge can be read. The edge is the secret. Look closely at the leaves of living plants, and you find two broad kinds of margin. Some are smooth, running in an unbroken curve from tip to stem. Others are toothed, notched with tiny serrations along their sides. Across the modern world, botanists noticed a quiet pattern in how these two kinds are shared out. In warm, wet forests, most trees carry smooth-edged leaves. In cooler forests, the proportion of toothed leaves climbs. The colder the mean annual temperature, the more teeth you tend to find in the canopy overhead. That relationship is the whole engine of leaf margin analysis. You do not measure a single leaf and read a number off it. You gather an assemblage, a whole fallen community of species from one layer, and you count. What fraction of the species have smooth margins? What fraction are toothed? You feed that proportion into an equation calibrated against living forests, and out comes an estimate of the mean annual temperature the fossil forest lived in. For the middle Eocene leaves of Seymour Island, that method gives a figure near 51 degrees Fahrenheit. Written more carefully, it is about 51, give or take 2 degrees. The estimate carries its uncertainty on its sleeve, because the leaves themselves are a scatter, not a single clean signal. Alongside that temperature sits an estimate of rainfall, roughly 60 inches a year, enough to soak a broadleaf and conifer forest, whose closest living cousins grow in the wet, moss-hung valleys of southern Chile and New Zealand today. Notice what that number is, and what it is not. It is a best current estimate, drawn from the physiognomy of leaves, the shape of them rather than any direct reading. Nobody stood in that forest with an instrument. The teeth on the leaves are the instrument, calibrated against forests we can still walk through and measure. That is why the answer arrives as a band and not a point. When you hear 51 degrees, you are meant to hear the give or take along with it. There is a second archive in the same rock, and it keeps a different kind of time. It lives inside the wood. Cut across a fossil trunk or a silicified stump, hold a slice under a hand lens, and the growth rings step into view, one pale band after another. Each ring is a single year of the tree's life, but the shape of those rings tells you more than how many years passed. In a growing season, a tree first lays down early wood, made of wide, thin-walled cells built quickly while conditions are good. Later in the season it lays down late wood, cells that are smaller and thicker walled, packed tight as growth slows toward winter. In most trees you have ever seen, that late band is dark and firm, a clear boundary where the cold or the drought closed the year down. The ratio of the two records how the growing season ended. Antarctic fossil wood breaks the familiar pattern, and that break is the finding. Ring after ring, the early wood runs wide and thin-walled, and the late wood is almost absent, a mere sliver or nothing at all. Read that under the lens and you're reading a very particular kind of year. These trees were not shut down by falling temperature or lack of water at season's end. They were shut down by darkness. They grew flat out through months of unbroken polar summer daylight, then stopped almost overnight when the sun went down for the winter, holding through the long dark and starting again when it returned. That makes these forests strange among the world's high-latitude trees. Modern forests near the poles are usually temperature limited. Their rings narrow when the summer runs cold. Antarctic wood tells you these forests were light-limited instead, paced by the polar rhythm of endless day and endless night rather than by the chill. You can hold that difference in your hand. Wide, pale bands with no dark edge. A tree racing the daylight, then waiting out the dark. There is a third reader of the past, and it does not need a leaf or a ring at all. It works from molecules cooked into ancient soil. In drill cores raised from Preids Bay, on the East Antarctic shelf, scientists hunt for a family of compounds called branched GDGTs. These are made by bacteria that lived in the soils of the old land surface, and the exact form they built depended on the conditions around them. The bacteria adjusted their own membranes to suit the temperature and the acidity they lived in, and those adjustments are locked into the molecules that survive. So you can grind a piece of ancient mud, extract these biomarkers, and turn their chemistry back into two readings. One is the temperature of the soil the bacteria lived in, the other is the pH, the sourness or sweetness of that ground. Across the Great Cooling near 34 million years ago, the Preids Bay biomarkers record soil temperatures falling from about 55 degrees Fahrenheit down to roughly 46, a drop of 9 degrees written in the fats of long-dead bacteria. The pH shifts in the same layers, rising from about 6 to about 6.7. On its own, that sounds like nothing. But a rise toward less acid soil, read together with the cooling, points to drying, to a land losing the steady wet that had fed its forests. Two independent dials on the same molecule, and both turn the same way, toward colder and drier. That is the kind of agreement that gives a proxy its confidence. Hold these three methods side by side, and you can see how a climate is actually rebuilt. The leaves give you mean annual temperature and rainfall from the shape of their margins. The rings give you the rhythm of the growing season and the reason it ended. The biomarkers give you soil temperature and soil chemistry straight from the ground itself. None of them is a diary. Each is a proxy, a stand-in, a careful translation from something preserved into something measured, and every one of those translations carries a stated uncertainty, on purpose. The 51 degrees for the Eocene forest is give or take 2. The 9-degree cooling in the biomarkers sits inside its own error bars. The honesty is the method, not a weakness in it. When a paleoclimatologist gives you a number, they are giving you the middle of a range they can defend, drawn from living forests and living bacteria that let them check their own work. Treat these figures as best current estimates, not as readings lifted from an instrument that was there. Which brings you back to the hands on the slope, because that is where it all still happens. The rock is split one hammer blow at a time. The leaf compressions are sorted by size and shape and laid out in trays. Someone leans close and compares a fossil margin to the leaves of a living relative, a beech from Patagonia, a podocarp from New Zealand, asking whether the teeth match, whether the venation runs the same way. A stem no thicker than a drinking straw is turned under a lens and its rings are counted one thin line at a time. A core of grey mud is sampled for molecules too small to see. This is slow, cold, unglamorous work, and it is the only reason any of these forests have a temperature at all. So when you picture the last Antarctic forests thinning toward the ice, remember that the thinning was measured, not guessed. Each stage left a signature that someone learned to read, and the clearest record of all lies offshore in the layered sediment on the sea floor, where the runoff of a dying land settled year by year into the dark. The forest did not vanish in a single winter, and what came next was a long, patient thinning you can still read in the mud beneath the sea. The forest did not vanish in a single winter, and what came next was a long, patient thinning you can still read in the mud beneath the sea. The forest did not vanish in a single winter, and what came next was a long, patient thinning you can still read in the mud beneath the sea. Off the coast of East Antarctica, drills have gone down through hundreds of feet of seafloor sediment. They come up carrying grey cores of compacted mud, and inside that mud lies pollen. Grain by grain, the pollen tells you what grew on the land upslope in the ages after the Great Cold began. So picture the map without the ice. Not a white dome, but a low dim country of stunted trees. This is Antarctica through the Oligocene and into the Miocene holding on. Stay with me here and let the scale of it settle slowly, the way sediment settles through still water. The picture that emerges is not a forest and not a barren. It is a mosaic. Across parts of East Antarctica, the vegetation had become a patchwork of southern beech and conifer, but shrunken, bent low, spread thin. In the pollen record you can see two families holding the ground. One is Nothofagus, the southern beech, the same lineage that clothes the wet slopes of the far south today. The other is the podocarp conifers, needle-leaved trees whose living relatives still grow in New Zealand and in Chile. Between them, in the low places, sat tundra, mosses, scrubby herbs, open ground where the wind never let a trunk stand tall. Scientists reach for a living comparison because the mind needs one. They point to the taiga-tundra transition, the frayed edge of the world's forests where trees give out and the treeless ground begins. You can find that transition today in southern Chile, along the cold, dripping fjord country near the tip of South America. You can find it again in southwest New Zealand, in the sodden, wind-raked lowlands below the peaks. Imagine that ragged border, that zone where woodland dissolves into moss and shrub, and lay it across an entire continent near the pole. That is roughly what the Oligocene mud describes. To feel how the change arrived, you have to go back to the doorway of it, to the moment just before the deep cold locked in. That record sits in Pridd's Bay, on the East Antarctic shelf, where the ocean drilling program pulled a core from a place called Site 1166. Down in that core, at a depth pinned to about 35.7 million years ago, in the late Eocene, the pollen changes character. It goes quiet. The diversity drops. What remains is a low, spare assemblage, dominated by Nothofagus, by the Araucaria conifers, and by the podocarps. Three families doing the work that dozens once shared. Read that assemblage carefully, and it describes a cool to cold temperate rainforest, thinning towards scrub. The trees were still there, but they were retreating into their hardiest members. The estimated mean annual air temperature comes out below 12 degrees Celsius, which is below about 54 degrees Fahrenheit. That is the yearly average. Remember the smear of warm summer and bitter dark winter pressed into one figure. The rain, or more often the wet snow and drizzle, still fell in quantity, somewhere between roughly 47 and 98 inches a year by the proxy estimates. So this was not a dry death. It was a cold, wet, dwindling life. Water was never the thing these plants lacked. What they lacked was warmth, and what they lacked was light for half the year, and against both they answered with a particular shape. That shape has a name borrowed from the mountains of the north. Krummholz. It means crooked wood. You have almost certainly seen it, even if you never knew the word. Go to any high mountain and climb toward the tree line, the altitude where upright forest gives up. Just below that line, the trees stop reaching for the sky. Instead, they crouch. Wind and cold press them flat, and they grow sideways, matted, hugging the ground like a thick green rug thrown over the rock. A spruce that would stand 100 feet tall in a sheltered valley becomes, up there, a knee-high tangle you could sit on. The branches on the windward side die back. The whole plant leans away from the prevailing gale, sculpted like a slow green flag. That is krummholz. And that is what much of Antarctica's beech and conifer became as the Oligocene cold settled in. Think about what that shape costs a tree, and what it buys. It costs height, and it costs light, because a low plant shades itself and its neighbours, but it buys shelter. Down in that matted layer, close to the soil, the wind speed drops and the temperature climbs a few precious degrees. Snow drifts over the whole low form in winter and becomes a blanket rather than a killing weight. The growing tips survive under it. When the long summer light returns, the plant does not have to rebuild a tall trunk. It just has to green the mat it already holds. Slow, patient, close to the ground. That is the whole strategy of survival at the edge of what a tree can bear. And it was slow. When paleobotanists later found actual wood from Antarctic beech of this hardy, ground-hugging kind, they counted the growth rings and found stems barely over a centimetre thick, about the width of a pencil, carrying more than 60 rings inside. 60 years of life in a stem you could snap between two fingers. A plant no taller than your boot that had been alive longer than most of the people who would one day dig it out. Hold that in your mind for a moment. The pace of a whole life, wound tight into a twig. Now the neat version of this story would draw a clean line. Forest, then cold, then nothing. But the real record refuses to be that tidy, and this is where the science stays honestly unsettled. In 2025, a study of plant macrofossils from West Antarctica pushed the survival of the southern beech family later than many earlier reconstructions had assumed. Not just pollen this time, but macrofossils, the larger fragments of leaf and wood that tell you a plant actually grew on the spot rather than blew in from far away. That work reported Nothophagaceae, the beech family, persisting as forest vegetation into the early Miocene. Sit with what that means. It means the trees hung on in places longer than the old timeline allowed. It means the last forest is not a single fixed date carved into the rock. It is a moving target still being pinned down. That 2025 result is new enough that researchers are still fitting it into the larger picture, weighing it against the drill cores and the pollen in the older sites. This is what living science looks like from the inside. Not a finished map, but a map being redrawn as fresh ground is opened. The honest answer to when the forest ended is that the answer is still moving. Before we follow the cold down its final slope, let me say one plain thing, gently, and then step back out of the way. If these long, quiet walks through deep time help you drift off, you can follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. That is all. Now let the ice come back into the picture, slowly, the way it actually came. Because the cold did not fall in a straight line either. It faltered. It warmed and cooled and warmed again, and one of those warm pulses matters enormously for the surviving trees. It is called the mid-Miocene climatic optimum, and it ran from roughly 17 to about 14.8 million years ago. For a few million years, the whole planet ran warmer than it does now, by an amount that the proxy estimates place at something on the order of 5 to 7 degrees Fahrenheit above today's global average. That does not sound like much when you say it fast, but spread across a cold, ice-loaded continent, a few degrees is the difference between an ice sheet that holds and an ice sheet that lets go. And let go it did, in places. During that warm pulse, the East Antarctic ice sheet is thought to have pulled back inland across the Wilkes Land Basin, a great low bowl of the continent that lies partly below sea level even today. As the ice retreated up and inland, it uncovered land that had been buried. Ground that had lain sealed under frozen weight came back into the air, into the returning light. And where there is bare ground, and a little warmth, and wind-borne spores and seeds, life follows. Vegetation crept back over the re-exposed land. Not the tall rainforest of the deep past, something lower, tougher, adapted to the margin, but green, again, for a while. Try to stand in that moment. The warm pulse of the mid-Miocene, the ice edge grinding slowly backward, and behind it a strip of newly opened country greening under a low sun. It is a reprieve, and you can feel that it is only a reprieve because you already know how the story tilts. The warmth was borrowed. The ice was waiting at the edge of the basin like a tide held back, and tides come in. This is the quality of the whole Oligocene to Miocene stretch that you have to hold on to. It was not one long slide. It was a stair, with warm landings and cold steps down. On the warm landings, the survivors spread a little and caught their breath. On the cold steps, the retreated, dwarfed further, gave up more ground, and across all of it the long trend ran one direction only, down toward cold, down toward ice. Each warm reprieve returned a little less than the one before, and each cold step took a little more than it gave back. You can read that stair in the very same cores that carry the pollen. As the cold steps deepened, the pollen from tall, temperate trees grows scarcer. The signal from mosses and hardy shrubs grows stronger. The picture in the mud tilts, decade by decade, age by age, from woodland toward tundra, from tundra toward bare and frozen ground. It is a slow motion you would never see in a single lifetime, or 1,000. It only appears when you stack the ages up and look down through them, the way the drill looks down through the seafloor. And here is the strange, quiet dignity of it. The trees did not lose because they were weak. They were extraordinary. To live at all where these lived, near the pole, through months of unbroken dark, in a cold that deepened across millions of years, is one of the great endurances in the history of plants. The southern beech and the podocarp conifers did not surrender the pole in a season. They defended it, foot by foot, for tens of millions of years, shrinking and crouching and slowing their whole way of living down to the barest flicker that still counted as growth. What finally took the ground was not a single catastrophe. It was patience on the other side, the endless patience of the cold. Think again of that pencil-thin stem with 60 rings. Every one of those rings is a summer that a tree stole from the ice, 60 stolen summers in a twig, and every ring is also thinner than the tree would have grown in a kinder world, because a kinder world was not on offer. That is what holding on looked like, not defiance in any loud sense. Just the same small green mat, greening again each time the light came back, for longer than you can easily imagine. By the time the mid-Miocene warm pulse ended, 14.8 million years ago, the reprieve was over and the ledger came due. The cold step that followed was one of the sharper ones in the whole record. The borrowed warmth was called back in, and the ice that had drawn inland across Wilkes Land came grinding forward again over the ground it had briefly freed. Whatever green had crept back onto that re-exposed land now stood in the path of returning ice, and the survivors were already about as small as a woody plant can be, and still be called a tree. There is a temptation, telling this, to reach for the language of tragedy, to make the trees mourn. But they did not know they were the last of anything. Each generation simply lived at the edge it was given, set seed if it could, and held the mat of ground it held. The tragedy, if there is one, belongs only to us, looking back down the cores, able to see the whole slope at once. The plants only ever saw the next summer, and for a very long time, against everything, the next summer kept coming. So follow the descent now with clear eyes. Out of the Oligocene mosaic of beech and dwarf conifer, through the flickering warm landings of the early Miocene, and down toward the middle of that period, the survivors are running out of options. The tall trees are already gone from most of the continent. What remains is the toughest fraction of the toughest fraction. Krummholz beech in the most sheltered pockets, conifers reduced to scrub, and below, even them, closing in, the mosses and the low tundra herbs that ask the least of the world and can therefore endure the most of it. You can watch, in the record, the centre of gravity shift downward. Earlier the trees were the story and the tundra was the margin between them. Now the tundra is becoming the story, and the trees are becoming the margin, the last woody holdouts, in a landscape going over to moss and gravel and cold. The forest is not being replaced by ice directly. It is being replaced by tundra first, and the tundra by ice after. There is an order to the undoing, a sequence you can trace, and it runs from tall to low to prostrate to bare. Let one slow breath mark the turn here, because this is the hinge of the whole descent. Everything before was a forest thinning, everything after is a tundra dying. The middle Miocene is where those two motions meet and change places. By the time you reach that hinge, the numbers have all bent the same way. The mean temperatures that once sat below 54 degrees Fahrenheit have slid lower still. The growing season that once ran through a long polar summer has shortened to a brief cool window, a few weeks when the ground thaws at the surface and life scrambles to do a year's living. The rain that once fell in the tens of inches gives way, more and more to snow that does not fully melt. And the light regime never changed at all. That strange polar clock of months of day and months of night, the one constant across the whole 100-million-year story, still ticking over a world with almost nothing left to answer it. What is left, at the hinge, is small, ankle-high, ground-hugging, the kind of life you would have to kneel to see, mosses in the damp low places, a last scatter of dwarf woody plants in the most sheltered valleys, where a fold of land broke the wind and held a little summer warmth against the rock. Everywhere else, the ground was going over to stone and ice, and the green was pulling back into the few corners that still, barely allowed it. It is worth pausing on how complete the coming reversal would be, because it lends weight to how much was still hanging on here. The same broad region that held these last damp, moss-fringed valleys would, in time, become some of the driest and coldest ground on the whole planet, a place that has likely not known meaningful liquid water for millions of years. But that final desert is not here yet. Here, at the middle Miocene, there is still moss. There is still, in the sheltered folds, a little green that has to be counted as forest's last kin, however small. That is the country we are descending into. Not the tall, dripping rainforest of the deep Eocene, and not yet the frozen desert of the age to come, but the narrow band between them, where the last real vegetation of continental Antarctica made its final, patient stand. The trees, as trees, are nearly spent. The tundra that replaced them is itself now under sentence. And the whole living cover of the continent has been squeezed, age by age, cold step by cold step, into a thinner and thinner ribbon of the possible. So let your mind come to rest at that threshold, with the warm pulse behind it, and the deep cold ahead. Picture the low sun over a folded, wind-scoured land. Picture the moss in the damp hollows, and the last dwarf scrub in the sheltered valleys, holding their small green ground against a cold that would not, in the end, relent. Everything grand has already gone. What remains is quiet and low and almost unbearably tough, and it is about to be tested one last time. Picture yourself set down inside that cooling world, somewhere along the East Antarctic coast, tens of millions of years after the tall rainforest first began to thin. The ground here does not climb into a canopy, it spreads. Everything that grows keeps its head low, pressed against the soil as if bracing against something. This is the Oligocene mosaic, and to stand in it is to stand inside a forest that has learned to lie down. Around your boots the southern beech grows sideways, nothofagus, The same family that once clothed the warm Eocene slopes still holds on here, but its shape has changed utterly. The branches reach outward rather than upward, matting across the cold ground in low, wind-combed tangles. Botanists call this form krummholz, a word for wood bent and flattened until a tree becomes a mat. You would see the same growth form today at the alpine tree line in the Andes or high in the Scottish Highlands, where the last stunted trees trade their height for survival. So the trees are still trees, they simply no longer stand. A conifer that might have risen 100 feet in a warmer age now hugs the earth at knee height, its trunk thick as your wrist, splayed flat and layered where the wind has laid it down. The podocarp conifers persist, the same southern family that still grows in New Zealand and Chile today. Scattered among them, in the pollen locked into East Antarctic drill cores, are traces of the Araucariaceae, the ancient conifer line that gave the world the monkey puzzle tree. The forest has not vanished. It has been pressed thin. Between these low mats of beech and conifer the ground opens. You would walk across patches of bare soil, gritty and dark, where nothing has managed to root. Then a stand of scleromorphic shrubs, their leaves small and hard and leathery, built to hold moisture and resist the drying bite of wind. Then a low wet hollow crowded with herbs, the boggy margin of a shallow pool. This is what a mosaic means on the ground. Not one continuous woodland, but a quilt of small worlds stitched together, each holding a different fraction of the light and the wet. Scientists who study the pollen from places like Pridd's Bay, on the East Antarctic shelf, read exactly this in the grains. A low-diversity community, beech and podocarp and Araucarian conifer, and little else. Not the crowded richness of the old rainforest, but a spare, cold hardy assemblage. They calculate a mean annual air temperature below about 54 degrees Fahrenheit for the late Eocene coast here, already sliding downward. Across the great cooling steppe that follows, soil temperature markers in those same cores fall from roughly 55 degrees to 46 degrees, and the land grows measurably drier as it chills. You would feel that cold not as a single number, but as a texture. The air here is raw and damp, and it moves. Wind is the sculptor of this whole landscape, the force that decides which way a tree may grow and how tall it is allowed to be. It comes off the strengthening cold ocean in long, patient pushes, and over decades it does to a beech what a hand does to grass, pressing it flat and holding it there. Every low mat around you is a record of that wind, written slowly into living wood. The rain, when it comes, is generous by the standards of a polar place. Estimates from the pollen and the sediments put the yearly total somewhere between roughly 47 and 98 inches, enough to keep the hollows wet and the moss thick underfoot. But it is cold rain, and cold mist, and long grey stretches of damp that never quite lift. If you knelt to touch the ground, you would find it spongy with moss and matted litter, holding water like a soaked cloth, the soil beneath it dark and sour and slow to drain. And then, folded through all of it, the strangest fact of this place, the one your body would never fully settle into. The light does not behave the way light should. For months in the polar summer, the sun does not set. It circles low around the whole rim of the sky, never dipping below the horizon, and the beech and the conifers photosynthesize around the clock, drinking a light that never switches off. Growth happens in one long, unbroken push. Then, over the far side of the year, the sun sinks and stays gone, and the land holds months of true dark, a stillness in which nothing grows at all. You can read that rhythm directly in the fossil wood, in the growth rings the trees left behind. The rings are dominated by wide, pale early wood, the loose, fast-grown cells of the endless summer, with almost no dark, tight late wood at the end. In most forests on Earth today, a growth ring is a story of temperature and drought. Here it is a story of light. These trees were limited not by heat or water, but by the sun itself, racing to build tissue while it shone, then shutting down entirely when the dark closed in. Try to hold both halves of the year in mind as you stand here. The summer version of this scrubland is almost tender, low and green and dripping, moss glowing under a sun that will not leave, insects working the wet margins of the pools. The winter version is the same ground gone black and silent, the beech mats frozen hard under a sky with no sun in it, everything waiting. The plants around your feet live through both, every year, and the wide then empty rings are the receipt. Wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice, let this cold, low forest settle around you for a while. There is no hurry in it. There was never any hurry in it. Because the honest thing to say is that most of what a place like this felt like is inference, not record. The rock preserves the pollen, the wood, the chemistry of the old soils. It does not preserve a sound or a smell. So when you imagine the noise of this scrubland, imagine it gently and hold it loosely. Not the layered roar of a tall rainforest, with its dripping tears and its calling canopy. Something lower and thinner. Wind moving across matted wood and open ground with no high leaves to catch it and turn it into that soft ocean hush. The trickle of meltwater through a boggy hollow. The small dry rattle of hard shrub leaves. Long stretches of near silence, the kind that only a sparse cold land can hold. The smell, if you let yourself guess at it, is the smell of cold, wet moss and peat, of sour, waterlogged soil and resin from the low conifers, sharpened by that constant clean bite of chilled sea air. It is a bog and a heath more than a jungle. Nothing sweet, nothing heavy, nothing tropical. A thin, mineral green-brown scent, the atmosphere of a place already halfway to tundra. Hold it as atmosphere, as the reasonable dream of a landscape, and not as something anyone recorded. What matters, standing here, is the shape of the change you're inside of. This is not a forest that has been struck down. It is a forest being slowly negotiated downward, trunk by trunk, degree by degree, ring by ring. The tall, wet rainforest of the warm ages has already been traded away. What remains is this taiga-tundra transition, a mosaic that the scientists who study it compare to the cold margins of southern Chile and southwest New Zealand today, where beech and conifer scrub gives way to open ground and heath. A living tree line laid almost flat, holding a coastline that grows a little colder and a little drier with each turn of the long polar year. And it holds. That is the quiet marvel of the Oligocene here. For a stretch of time, far longer than you can truly feel, this pressed-down forest keeps its footing. The beech mats keep leafing out under the endless summer sun. The podocarps keep laying down their wide, pale rings. The wet hollows keep filling and freezing and filling again. Life does not surrender the pole, it only lowers itself and narrows and learns to want less. But the trend beneath it all runs one way. Each cold step trims a little more height, thins a little more of the canopy that is barely a canopy at all, opens a little more bare ground between the mats. The scleromorphic shrubs gain where the trees lose. The pollen counts grow leaner, the rings grow narrower. Stand here long enough, across time you could never actually stand across, and you would watch the beech give up even its low sprawl. Watch the conifers pull back into the last sheltered pockets. Watch the open ground widen until the mosaic is more gap than growth. The forest that learned to lie down is slowly learning to disappear. By the middle Miocene, the tallest survivors had shrunk to a carpet of moss and low scrub clinging to a few sheltered valleys. By the middle Miocene, the tallest survivors had shrunk to a carpet of moss and low scrub clinging to a few sheltered valleys. By the middle Miocene, the tallest survivors had shrunk to a carpet of moss and low scrub clinging to a few sheltered valleys. You have followed the forest down a long stairway of cold, from rainforest to woodland to dwarfed thickets. Now you arrive at the last landing but one. Picture a bench of high ground above a broad glacial trough, a place today called the Fries Hills, standing over Taylor Valley in the McMurdo Dry Valleys of East Antarctica. You are near 2,000 feet up, on gravel and old lake beds, in air that has already forgotten what a tree feels like. Look down at your boots. There is no canopy here, no trunk, no shade. There is only the ground, and the ground is quietly, stubbornly alive. Kneel. Bring your face close to the surface, the way a paleobotanist does when the light is low and flat. What survives here is small enough to miss. Mosses, first of all, matted into low green cushions across the damp margins of shallow lakes. Around them, in the fine sediment, lie the shells of ostracods, seed shrimp no larger than a grain of coarse sand, each one a tiny two-part case that opened and closed in still water. There are diatoms, single-celled algae in glass houses of silica, so small that thousands would fit across your thumbnail. And there are insects, or the fragments of them, wing cases and hardened parts pressed into the mud. This is a whole community, and every member of it is built low to the ground. Hold that picture because it is the important one, a landscape without a single tree, yet not a dead landscape. The lakes were shallow and cold, fed by summer melt, rimmed with moss and sedge and the faint traffic of small living things. This is the mid-Miocene tundra of the Fries Hills, and the fossils that record it have been dated to more than 14 million years ago. It is, as the researchers who described it put it plainly, the last vestige of tundra vegetation in continental Antarctica. After this, the interior of the continent stepped down into a fully polar climate, and it has never climbed back out. To feel what this place was, you can borrow a living example from the far north. The scientists who studied the Fries Hills reached for southern Greenland as the closest modern match. Imagine that. A low, sparse, cold country of moss and shallow water, and short summers, treeless but not lifeless, where growth is measured in fractions of an inch and patience is the only strategy that works. That is the register you want in your mind. Not the green cathedral of the Eocene Peninsula, not the wet fern floors under 60 inches of rain, but a thin skin of hardy life spread over frozen ground, holding on through the brief warm weeks and waiting out the rest. You should feel the smallness of the margin. Tundra lives in the narrow seam between land that is too cold for it, and ice that would erase it entirely. In the Fries Hills that seam was already closing. The plants and animals preserved in those old lake beds were not thriving so much as persisting, drawing what they could from a few weeks of thaw, then shutting down under the long dark. For a landscape this far south, simply to stay alive from one summer to the next was an achievement written into every layer of mud. There is a reason this particular bench of ground matters so much to the people who study Antarctica's past. Higher ground in the dry valleys can hold surfaces that are astonishingly old, protected from the grinding of thick ice, left to weather slowly in the dry cold. The Fries Hills sit above the modern valley floor like a shelf that time forgot to clear. On that shelf the ancient lake sediments were buried, capped and preserved, rather than scoured away. So when you look at those moss cushions and ostracod shells, you're looking at a snapshot that the continent against long odds managed to keep. Now lift your eyes from the ground to the work being done here in the present. The end of Antarctic tundra is not a settled line on a chart. It is a research problem, and there are scientists actively drilling for the answer. The Fries Hills Drilling Project, led by Richard Levy and Tim Naish, set out to recover a continuous core through these old lake beds, a single unbroken column of sediment that could be read layer by layer. A scattered fossil here and a fragment there can tell you that tundra existed. A continuous core can begin to tell you when it ended, and how quickly, and whether the cold came as one clean drop or as a staircase of colder and colder steps. Think about what a continuous core actually is. It is a cylinder of ancient mud and sand, pulled up from below in sections, each section a stack of seasons and centuries laid down in order. Read from bottom to top, it runs forward through time. In it, A specialist can count the diatom species that come and go, watch the mosses thin, track the chemistry of the water as it cooled and dried. The Freese Hill's core is meant to catch the exact interval when a living tundra crossed over into frozen sterility. That is the moment the drillers are chasing, and it is being chased right now by people who fly to the ice, set up their rigs on that high bench and bring the frozen record home. There is something worth sitting with in that image. The continent that killed these forests is now the reason we can study them. The very cold that ended the tundra also sealed and froze its remains, holding the moss and the seed shrimp and the glass-shelled algae in place for 14 million years until a drill came looking. You are, in a sense, watching two kinds of patience meet. The slow patience of the fossils waiting in the dark and the deliberate patience of the science, reading them one thin layer at a time, so the Freese Hills give you a firm anchor. Around 14 million years ago, in the interior of East Antarctica, the last tundra we can clearly point to went quiet. The mosses stopped. The lakes froze over and stayed frozen. The stepped cooling of the middle Miocene pushed the inland climate past the point where even ground-hugging plants could hold, and the door closed. If you wanted a clean, tidy ending to the long tail of Antarctic vegetation, you could stop here, and many summaries do. 14 million years, the last green thing in the heart of the continent gone, but the ending is not clean, and honesty requires you to say so. The Freese Hills record the last tundra in the continental interior. It does not necessarily record the last plant life anywhere on the continent's edges and high spines. And this is where the tale opens into a real and unresolved question, the kind that working scientists still argue over in print. Was 14 million years ago the true end? Or did something even smaller, even tougher, hang on somewhere higher and colder and farther south for millions of years more? The problem is genuinely open. On one reading, the mid-Miocene tundra extinction is the end, full stop, and anything younger is either misdated or misread. On another reading, the interior went cold while a few favoured pockets, closer to the mountains that ring the polar plateau, kept a thread of life going into far more recent time. You cannot settle this by wanting one answer. You can only lay out what has been found and where, and let the disagreement stand as what it is, a live edge of the science rather than a closed chapter. To follow that thread, you have to leave the dry valleys and travel deeper into the Transantarctic Mountains, the long rampart of rock that separates East Antarctica from the Ross Sea. This range runs for well over 1,000 miles, a spine of peaks and glaciers that the ice sheet presses against and spills through. Somewhere along that spine, in a rock unit called the Sirius Group, lies the material at the centre of the whole argument. And it is not moss this time, it is wood, it is leaves, it is beech. Here you should slow down, because this is the youngest confirmed forest material anyone has found on the continent, and it deserves a careful eye. In glacial deposits high in the mountains, at a locality called Oliver Bluffs in the Dominion Range, geologists working through hardened until recovered stems, twigs, leaves and wood of a dwarfed southern beech. The plant was named Nothofagus beardmorensis, a new species described from these fossils. It was not a tree in any shape you would recognise from a temperate hillside. It grew flat, prostrate, hugging the frozen ground, a form botanists call krummholz, the bent and matted growth that wind and cold force on trees at their absolute limit. Take the measure of it, literally. The fossil stems of this beech reach a maximum diameter of only about half an inch, yet inside that slender wood, under a hand lens, sit more than 60 growth rings. Read that slowly. A stem no thicker than a pencil, carrying 6 decades of life packed into its rings. These were not saplings cut down young. They were mature plants that had simply grown that slowly, adding a hair's width of wood each short summer for longer than a human lifetime before the cold and the ice finally took them. A whole beech, older than 60 years, that never rose higher than the top of your boot. Let that sit against everything you have followed so far. The tall podocarp forests of the Eocene, the wet broadleaf canopies within a few degrees of the pole, the woodlands that thin to scrub. Now the whole grand descent narrows to this. a ground-level tangle of beech spreading sideways because it could not spread up, counting out its slow decades in rings finer than thread. If any single object could stand for a forest at the end of its endurance, it is this pencil-thin stem with 60 summers inside it. Wherever you're listening, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. The climate these dwarf beeches lived in was harsh, but not quite as harsh as the same ground is now. From the growth rings and the leaves, researchers estimate that the site once had at least 2 to 3 summer months a year warm enough for growth, at mean temperatures around 39 to 41 degrees Fahrenheit. That is cold. It is also warmer than Oliver Bluffs experiences today, where nothing of the kind could grow. So the fossils record a window, a stretch of time when this high mountain flank was frozen for most of the year yet thawed just enough, just long enough, to let a stubborn beech creep across the gravel and hold its ground. You might ask how anyone dates a smear of till so high in the mountains. Part of the answer lies in tiny marine fossils mixed into the deposit. The Sirius Group beech material is associated with recycled marine diatoms, single-celled algae with silica shells, whose known ages constrain the deposit to no older than roughly 4 to 3 million years. That points to the Pliocene, a slice of time far younger than the Fries Hills tundra, only a few million years before the present. If that reading holds, then a forest, however tiny, was still alive on the continent long after the interior tundra had gone silent. And that is exactly where the controversy lives, because those very diatoms are read 2 ways by 2 camps, and the disagreement has run for 3 decades. This is not a settled date dressed up as a debate for drama. It is a real, named, documented argument between serious scientists, and the fair thing to do is to give you both sides and let them stand. On one side stand the researchers often called the stabilists, among them George Denton, David Marchant and David Sugden. Their argument runs like this. The East Antarctic ice sheet, they say, has been cold and largely stable for at least 15 million years. In their reading, the mountains have been locked in polar cold since the Middle Miocene, and there was no recent warm window in which a beech could grow at Oliver Bluffs. The young marine diatoms in the till, they argue, did not grow there, were not carried there by a collapsing sheet. Instead, they were blown in by wind from distant marine sources and settled into an older deposit, contaminating it with a false youth. In that view, the beech itself is older than the diatoms suggest, and the continent's deep freeze goes back much further than 3 million years. On the other side stand the researchers often called the dynamicists, among them Peter Webb and David Harwood. Their argument runs the other way. They read the Pliocene marine diatoms as being in place, genuine components of the deposit rather than wind-blown intruders. If the diatoms are truly of that age and truly belong, then the deposit itself is young, and the ice sheet that carried it must have been anything but stable. In their reading, the East Antarctic ice sheet collapsed and reformed as recently as around 3 million years ago, opening seaways in the interior and in a warmer interval, allowing dwarf beech to grow high in the Transantarctic Mountains, before the ice returned and buried it. You can see why this matters far beyond one twig. If the stabilists are right, Antarctica's great ice sheet is an ancient, sluggish, deeply reliable thing, unmoved for 15 million years. If the dynamicists are right, that same ice sheet is capable of dramatic collapse on timescales that should give anyone pause. The little beech at Oliver Bluffs is not just a botanical curiosity. It is a proxy for one of the largest questions you can ask about the polar south, which is how stable that ice truly is and how fast it can change. The forest and the ice sheet are arguing the same case. Hold both positions at once without forcing a verdict. The evidence is a deposit of hardened till containing dwarf beechwood and leaves, plus marine diatoms that look Pliocene in age. One camp says the diatoms blew in and the setting is ancient and stable. The other says the diatoms belong and the setting is young and dynamic. Both camps are reading the same rock. Both have built careful cases, and the fair statement, the honest one, is that the age and meaning of the Sirius Group remain genuinely debated. This documentary is not the place to declare a winner, and the science has not declared one either. So the neat number you might have wanted, a single date for the last forest in Antarctica, dissolves a little in your hands. The Sirius Group beech is the most commonly cited candidate for the youngest confirmed Antarctic forest, often placed around 3 to 4 million years ago. But whether that Pliocene date is the true age, or whether the material is older and only looks young, is precisely what is unresolved. Some researchers would put the real end of Antarctic forest cover earlier, tied to that mid-Miocene tundra extinction, around 14 million years ago, with the Pliocene beech representing either a genuine late survival or a reworked older deposit. The last forest, in other words, is a moving target in the literature, not a fixed line in a textbook. It is worth pausing on how alive this question still is. Even now, new material keeps shifting the picture. A recent study of plant macrofossils from West Antarctica documented southern beech family forest vegetation persisting into the early Miocene, extending the known window of forest survival later than some earlier reconstructions had assumed. That single result did not close the debate. It added a data point that scientists are still working to fit into the larger timeline. The lesson you should take is not a tidy answer, but a truer feeling for how this knowledge is made, in increments, in argument, in the slow accumulation of one more sample from one more frozen outcrop. Now come back to the ground itself, to the physical texture of where these fossils sit, because the setting tells you much about why the debate is so hard to settle. The Sirius Group is glacial till, and till is a rough, unsorted mix. Picture it. Gravel and sand and pebbles jammed together, ground and carried and dumped by moving ice, then hardened over time into a stony, gritty matrix. Into that coarse material the delicate beech leaves and slender twigs are pressed, fragile things caught in a rock made of grit. When a geologist wants one, the tool is a hammer, and the work is the patient rasp of steel against stone, splitting the till to expose a leaf compression no bigger than a fingernail. You should feel that grit under your hand. This is not the fine, quiet mud of the Fries Hills lakes, where a moss cushion settled softly into still water. This is wind-driven, ice-driven material, high above the valley floor, embedding fragile fossils in gravel. The very roughness that makes the deposit hard to date is the roughness of ice at work, scraping, carrying, dropping its load. Every pebble in that till was moved by cold. And somewhere in the mix, a beech leaf that once caught a few weeks of pale summer sun waits to be found, its outline intact, its message ambiguous, its age still argued. Stand up now and take in the wider scene one last time before this segment closes. Below you, the dry valleys stretch away among the driest and coldest ice-free places on Earth, ground that has likely not seen significant liquid water for millions of years. The wind here is a hyper-arid, near-waterless wind, and it bites. Yet this is the same country that once held the moss-fringed Miocene lakes of the Fries Hills, and the same mountains that may have sheltered the dwarf beech of the Sirius Group. The contrast is total, and it is the whole point. A land that carried some form of forest for more than 200 million years is now, in its heart, as close to lifeless as any place on the planet. You have traced the long decline nearly to its end. From rainforest to woodland, from woodland to scrub, from scrub to a treeless tundra of moss and seed shrimp and glass-shelled algae, and finally to a scatter of pencil-thin beech stems that may or may not mark the very last stand. The interior fell silent around 14 million years ago in the Fries Hills, where the last clear tundra went quiet under a stepped and stubborn cold. That much you can hold with some confidence. The rest, the question of whether life crept on higher and later, remains open, the kind of open that the fossils themselves refuse to close. So let the interior stand as it is, frozen and certain, the tundra long since gone silent under the ice, Let the moss cushions and the seed shrimp settle back into the dark of their old lake beds, their record read and still being read, layer by patient layer, by the drillers on the high bench above Taylor Valley. Consider the trouble scientists have with a single word, last. When did the last Antarctic forest actually die? You might expect a date carved somewhere, a clean line drawn under the final tree. Instead, there are 3 candidate endings set at 3 very different depths of time. The people who study them do not agree on which one counts. The oldest of the 3 endings sits near 14 million years ago, in the mid-Miocene. The place is the Fries Hills, a cluster of low rises about 2,000 feet above Taylor Valley, in the McMurdo Dry Valleys of East Antarctica. In old lake beds there, researchers recovered a quiet catalogue of life. Cushions of moss, freshwater diatoms, the wing scraps of insects, the paired shells of ostracods, seed shrimp no bigger than a grain of rice. A tundra, in other words, low and damp and treeless, its closest living match the tundra of southern Greenland today. Writing in 2008, Lewis and colleagues called this the extinction of tundra in continental Antarctica. After it, the interior tipped into a fully polar climate and did not come back. Read that deposit one way, and it becomes the true ending. Not the last forest exactly, but the last living ground cover of any kind in the heart of the continent. The reasoning behind it is the reasoning of steady one-directional cooling. By this account, the tall rainforests were already gone tens of millions of years earlier. Dwarf scrub lingered in sheltered pockets, thinner with each cold step, and by 14 million years ago even that low patient vegetation failed, snuffed out as the ice locked the interior shut for good. If you hold to that view, it carries a hard consequence. Anything that looks younger can't really be younger. It must be old material moved out of place, plant fragments quarried from an ancient bed and dragged downhill inside advancing ice, then dropped somewhere new. The plants would be real. Their apparent youth would be an illusion of transport. This is a defensible position, and serious scientists hold it. Ice is a thief that does not respect the order of layers. It can lift the deep past and set it down looking freshly buried. Now set a second marker on the table, much closer to us in time, and watch the neat picture bend. In 2025, a study of neogene plant macrofossils from West Antarctica reported something the strict cooling story did not predict. Fossils of the Nothophagaceae, the southern beech family, persisting into the early Miocene. This is the far side of the continent from the Fries Hills, a different basin with its own history of ice. And the fossils are macrofossils, pieces of the plants themselves, not just wind-blown pollen that could have drifted from somewhere warmer. They push the known window of Antarctic forest survival later than several earlier reconstructions had assumed. Here is why that matters, and why you should sit with it rather than file it away. A pollen grain can travel. It can ride wind and water for hundreds of miles and settle in a place the parent plant never grew. A leaf, a twig, a scrap of wood is heavier and clumsier. It tends to fall near where it lived. So macrofossils carry a kind of testimony that pollen alone does not. When they say a forest stood here, the claim is harder to wave away. The early Miocene beech of West Antarctica is a fresh data point, and like most fresh data points, it is still being folded into the larger timeline. It has not settled the argument, it has widened it. Because now you have 2 honest positions pulling against each other. One says continental Antarctica went treeless, and then lifeless in the deep interior by the mid-Miocene, and stayed that way. The other says forest vegetation, at least in some coastal or lower-lying refuges, held on later than that, into the early Miocene at minimum. Both rest on real fossils. Both are argued by careful people. The difference is not sloppiness. It is that Antarctica is enormous. Its ice cover is patchy in what it preserves and what it destroys, and a single continent can die in one region while it endures in another. And then there is the third marker, the boldest and the most disputed. It reaches all the way into the Pliocene, to something on the order of 3 to 4 million years ago. That is the youngest age anyone seriously proposes for living Antarctic forest, and it comes from the Sirius Group of the Transantarctic Mountains. The plant at its centre is a dwarf southern beech, a ground-hugging shrub that grew slower than almost anything alive today. The dating hangs on tiny marine diatoms mixed into the glacial deposit, single-celled algae in shells of glass, which point to an age no older than roughly 4.1 to 3.1 million years. The whole quarrel turns on those diatoms, and it is worth understanding the shape of it without picking a side. If the diatom settled into that deposit at the time it formed, then the deposit is genuinely Pliocene, and the beech in it lived in the Pliocene, and the last Antarctic forest survived astonishingly late, a few hundred miles from the South Pole. But if the diatoms were lofted by wind from marine sediments elsewhere and sprinkled onto much older ground, then the young date is borrowed, not earned, and the beech could be far more ancient than it looks. Same fossils, same glassy shells under the same microscope, two readings that differ by millions of years. You can feel how much rides on a thing so small. A diatom is invisible to the naked eye. Whether it drifted in on the wind or was buried in place decides whether Antarctica held a forest in the Pliocene or lost its last trees an age earlier. That is the strange scale of this science. The endpoint of a continent's forests, a question you would think as large as the sky, comes down to the travel history of a speck of glass. So there is no single settled date, and it would be a small dishonesty to pretend otherwise. Depending on which marker you trust, the last Antarctic forest died somewhere between about 14 million and about 3 million years ago. That is a spread of roughly 11 million years, longer than the entire span of human evolution, packed into the meaning of one word: last. Notice too that these three endings are not simply rival guesses at the same event. They may be measuring different things. The Fries Hills record the death of tundra in the deep interior, the treeless final scrub of the continent's cold centre. The West Antarctic macrofossils record forest survival in another region entirely, on a different timetable. The Sirius beech, if the young date holds, records a late surviving pocket high in the mountains. The very last huddle of woody plants anywhere on Earth at that latitude. A continent does not have to end all at once. Its forests could have retreated and winked out region by region, refuge by refuge. So that asking for one date is like asking when a fire went out when it had many embers, each dimming on its own clock. This is what live science looks like from the inside, and it is worth letting it stay unresolved in your mind rather than reaching for a tidy answer. No camp has won. The 2025 West Antarctic find is new enough that its full weight is still being tested against the older records. The Pliocene claim has been argued for decades and remains genuinely open. The mid-Miocene extinction is well documented, yet cannot by itself rule out survival somewhere it did not sample. The last forest of Antarctica is not a fact you look up. It is a moving target, its position shifting as new cores come up from the ice and new fossils come out of the till. And if you had to name the most conservative, honest flaw, the safest thing anyone can say for certain, it would sit back near that mid-Miocene collapse. By roughly 14 million years ago, the deep interior had gone cold and treeless and would remain so. That much the Fries Hills tundra makes plain. Everything younger than that is where the argument lives, where the diatoms drift and the dating splits, where reasonable scientists read the same glassy shells and walk away with answers millions of years apart. And yet, higher and colder still, one last stand of beech may have held on for millions of years more, in a place that still divides the scientists who study it. And so the last of them held on, higher and colder than any forest that had come before. That final stand of beech clung to a place that still divides the scientists who study it, and it deserves to be met slowly. Picture the slope where it grew, some 3 to 4 million years ago, a few hundred miles from the South Pole. The trees there rose no higher than the top of your boot. They did not stand upright at all. They spread sideways across the frozen ground, branches matted flat and low, hugging the thin soil the way heather hugs a windswept hill. This was beech, southern beech, the same broad family whose relatives still grow in Chile and New Zealand today. But nothing about this beech would look like a forest to your eye. There was no canopy overhead, no shade, no trunk you could set your hand against. There was only a dense, ankle-deep mat of woody stems, green in the brief summer, bare and grey through the long dark. You could have walked across the whole of it without once looking up. For most of the year the slope was locked in cold. Then, for a short window, the light returned. 2 months, perhaps 3. Warm enough for the leaves to unfold and the wood to add a thin band of new growth. Snowmelt trickled between the stems, small pools gathered in the hollows. The beech drank the meltwater and the endless summer light, and it grew, though only barely, only a hair's width in a season. Then the dark came back down over the pole, and the leaves fell, and the plant shut itself down and waited. Hold that image, because everything that follows is built on it. This is the youngest forest Antarctica is known to have grown. Not a rainforest, not a woodland, not even a proper thicket. A low huddle of dwarf trees surviving at the ragged edge of what a tree can do, in a place already halfway to becoming the frozen desert it is now. The fossils that record it come from a single stretch of the Transantarctic Mountains at a locality called Oliver Bluffs in the Dominion Range. The rock there is part of the Sirius Group, and the layer that holds the beech is called the Maya Desert Formation. It is glacial till, crushed and jumbled debris that ice leaves behind when it grinds forward over the land. Inside that till, mixed with the gravel and the groundstone, lie the remains of the plants the ice carried away. The most famous of those remains is a twig. It is a small thing, easy to overlook. Split from the surrounding rock, it measures barely half an inch across, no thicker than a pencil. You could close your hand around it and forget it was there. And yet, held under a lens, that thin stem tells a startling thing about itself. Packed inside its half-inch of wood are more than 60 growth rings. Sit with that number for a moment. More than 60 rings, in a stem you could snap between 2 fingers. Each ring is 1 year of life, 1 brief summer of growth followed by 1 long winter of stillness. This plant, no taller than your boot, was older than most human lives. It lived 6 decades and more on that cold slope, and in all that time it thickened by less than the width of your thumb. It was not young. It was not a seedling caught by a sudden frost. It was a mature plant, fully grown, and this slow, stunted, ancient form was simply what a mature tree looked like there. The species has a name, Nothofagus beardmorensis, described formally in 1996 from these very fossils, from leaves and wood gathered in the Sirius Group. It was a deciduous dwarf beech, a shrub really, growing in what botanists call a krummholz habit. Krummholz is a word worth knowing, because you can still see it in the world today, at the tree line high in the Andes or the Scottish Highlands, where wind and cold flatten the last trees into low, twisted mats. The word means crooked wood. That is what this was. Crooked, ground-hugging wood, bent by decades of wind into a shape that could survive. The growth rings say more than age. Read closely, they carry a fingerprint of the light. In these polar woods, the summer band of wood, the early wood, is wide and pale and thin-walled, laid down fast during weeks of unbroken daylight. The winter band, the late wood, is almost absent, because there was almost no autumn slowdown, only light, and then sudden dark. It is a growth pattern driven not by temperature but by the polar cycle of day and night, and it is unlike almost any forest alive today. From the leaves and the wood together, researchers have tried to read the climate that allowed this beech to live at all. Their best estimate is sobering in its thinness. At least 2 to 3 months a year, the site had to warm to a mean around 39 to 41 degrees Fahrenheit. Not warm, just barely above freezing for a short summer season, enough to melt snow and drive a trickle of growth. And here is the quiet shock of it. That is warmer than the same spot in the Transantarctic Mountains is today. The place that once held a living forest, however stunted, is now too cold and too dry to hold even this. Take a slow breath and let the scale settle. Ankle-high trees, 60 rings in half an inch, a summer barely above freezing, a forest measured not in the height of its canopy, but in the patience of its survival. This is the last stand, the final fragment, the thinnest thread of green Antarctica ever pulled through the cold before the thread was cut. Now comes the hard part, and it is the part that has kept scientists arguing for more than 30 years. How old is it exactly? When did this last forest actually live? The dating hangs on something small and strange. Mixed into the same glacial till as the beech are the microscopic shells of diatoms, single-celled algae that live in the sea and build delicate glassy skeletons. These are marine diatoms, ocean creatures, and yet here they are, ground into land-based glacial debris high in the mountains. Some of those diatom species are known only from the Pliocene, a slice of time roughly 2 to 5 million years ago. Their presence sets a ceiling on the deposit. The till, and the beech inside it, can be no older than about 4 to 3 million years. On that much, the fossils seem clear, but a ceiling is not a certainty, and this is where the calm agreement ends. The diatoms are the whole problem. Everything turns on one question. How did ocean algae end up in mountain till hundreds of miles from open water, and what does their presence really mean? This long argument even has a name. Scientists call it the Sirius debate, and it has run for 3 decades between two camps who read the very same rock and reach opposite conclusions. Let me lay both sides out fairly because neither has been proven wrong, and the honest answer is that the matter is still open. On one side stand the researchers often called the stabilists. Among them are George Denton, David Marchant and David Sugden. Their view is that the East Antarctic ice sheet has been cold and stable, and largely unchanged for at least 15 million years. In their reading, the interior of the continent froze hard in the middle Miocene and simply stayed that way, a vast, still, permanent cap of ice that has never seriously melted since. If that is true, then the beech cannot have lived 3 million years ago, because 3 million years ago this place was already deep beneath ancient ice. So how do they explain the Pliocene diatoms in the till? Their answer is the wind. Antarctic winds are ferocious and endless, and they argue that these tiny glassy shells were lifted from marine sediments elsewhere, carried aloft and blown for great distances before settling into the mountain deposits long after the beech had died. In this view, the diatoms are travellers, not residents. They drifted in on the air, and they date only their own arrival, not the rock around them. The forest itself, the stabilists suggest, is much older, a relic of the Miocene, and the young diatoms are simply dust that landed on top of a far more ancient grave. On the other side stand the dynamicists, and their leading voices include Peter Webb and David Harwood. They read the same diatoms very differently. To them, these marine microfossils are not wind-blown intruders, but in-place evidence, laid down where they lived, in seaways that once reached far inland. If the diatoms are genuinely part of the deposit, then the deposit is Pliocene, and so is the beech. And that carries a stunning implication. It would mean the Great East Antarctic ice sheet did not sit still and frozen for 15 million years at all. It would mean the ice collapsed, that the interior warmed and melted and opened to the sea, that beech forest returned to ground that had been buried, and that all of this happened as recently as about 3 million years ago, before the ice came back and closed over everything once more. You can feel how much rides on it. One camp sees a continent locked in a deep, ancient, unbroken freeze, its buried forests old ghosts. The other sees a continent that heaved and thawed and grew trees again within the last few million years, a far more restless and unstable ice sheet than the frozen calm suggests. The same twig, the same till, the same glassy shells, and two histories of the whole polar cap that could hardly be further apart. This is a good moment to remember something about how this record reaches you at all, and to pause the argument for just a breath. Follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Then let us step back into the quiet of the deep past, because the debate is not finished, and honesty asks us to hold it lightly. I'm not going to tell you which camp is right, because the science has not settled it. What I can tell you is where the weight of citation tends to fall and how carefully working researchers speak about it. The figure you will most often see attached to the Sirius Group beech is around 3 to 4 million years, the Pliocene. That is the most cited estimate for the youngest confirmed Antarctic forest material. But you should hear that number the way the scientists mean it, not as a fixed date carved into the record, but as a best current reading of a genuinely contested deposit. And there is a second layer of doubt underneath the first, one that touches the whole idea of a single last forest. Some researchers argue that the true end of Antarctic vegetation came earlier, out at the mid-Miocene tundra collapse, around 14 million years ago, when the last true tundra ecosystems went dark on the continent. In that reading, the Pliocene beech is either a remarkable late survivor, holding on for millions of years past the general extinction, or it is older material reworked by ice and redeposited into younger-looking till. Whether the last forest died 14 million years ago, or 3 or 4 million years ago, is not, as it turns out, a question anyone can yet answer with confidence. The last forest is a moving target, still being tracked by working scientists today. So we hold two numbers at once, and we let neither harden into false certainty. 3 to 4 million years, most often cited for the youngest confirmed forest remains. 14 million years, argued by some, for the true and final extinction of Antarctic vegetation. The truth may lie at one end, or the other, or somewhere in the shifting ground between them. That uncertainty is not a failure of the record. It is the honest shape of the record, and it is worth resting in rather than rushing past. There is one more discipline worth keeping as we stand beside this last beech, and it is a discipline of restraint. It would be easy, and it would be wrong, to fill this dwarf forest with animals, to place some small mammal picking through the leaf litter, or an insect droning in the brief summer air, or a bird crossing the pale sky above the mat of stems. The fossils here do not support that. What Oliver Bluffs preserves are plants. Leaves, wood, pollen, and the twig with its 60 rings. The animal life of Antarctica in these last cold ages is known from other places and other rocks, not from this beech stand. So we leave the slope as the fossils leave it, quiet and vegetable and still, a forest of dwarf trees and meltwater and silence, with nothing moving through it that the stones can vouch for. Let that restraint be part of the calm. You do not need to crowd the scene to feel its weight. An ankle-high beech, 60 years old and half an inch thick, growing 2 summer months a year at the edge of the ice, a few 100 miles from the pole. That is enough. That is more than enough. It is one of the strangest small facts in the whole long story of life at the ends of the earth, and it asks for nothing but your attention. Come back now to the twig itself, the pencil-thin stem where we began, because it is time to understand it fully. When you first met it, it was only a curiosity, a small piece of wood with an improbable number of rings. Now you know what it is. It is the physical proof of the last forest Antarctica ever grew, or at least the youngest such proof anyone has yet confirmed. It is a fragment that survived by accident, crushed and carried inside advancing ice, dropped into till, and preserved by the very cold that killed the tree it came from. Turn it over slowly in your mind. Half an inch of wood, 60 summers of light, 60 winters of dark, each one written into a ring so thin you need a lens to count it. A plant that lived longer than a human life and never grew taller than your boot. It stood on a slope that was already too cold for a real forest, in a place that would soon be far too cold for any forest at all. It was not the beginning of anything. It was the end. The last, slow, patient green thing on a continent that was about to go entirely white. For nearly 100 million years, Antarctica had carried forest in some form. tall rainforest on the peninsula, dwarf conifers and southern beech through the long cooling, tundra where the trees gave out, and then, at the very last, this. A mat of ankle-high beech on a mountain slope, waiting each year for a summer that barely came. When you hold the twig, you're holding the final page of that account, the thin edge where a forested pole became an icebound one. The scientists are still reading that page. The serious debate is not a closed matter in a textbook. It is a live disagreement between named researchers who have spent careers on it, and the drilling and dating go on, in the mountains and in the dry valleys, as this history keeps being written. Whether the last beech lived 3 million years ago or 14, whether the great ice sheets sat still or heaved and collapsed and came back, these are open questions handed forward to the people working on them now. But on one thing every camp agrees, and it is the thing that lets us close this chapter gently. The forest ended. The dwarf beech did not merely fade away into some milder future. The cold that had thinned it for tens of millions of years finally finished the work. The summers grew too short and too weak, the meltwater stopped, and the last mat of stems on the last cold slope went bare and did not green again. Consider how little the evidence actually was. Picture a slab of Sirius Group till, grey and hard, the colour of old cement, cold enough to numb a bare hand in seconds. The tool is a rock hammer, the work is slow. You tap along a seam and listen, and the rock parts, and most of the time nothing waits inside. Then, once in a long while, a face splits clean, and a leaf lies pressed against the stone, no bigger than a fingernail. A dark stain in the shape of a small blade, with a run of tiny teeth along one edge, the last hint of a plant that lived a very long time ago. That is how the youngest forest on the continent came to light, not in one dramatic stroke, but in fragments the size of a thumbnail. The place is Oliver Bluffs, in the Dominion range of the Transantarctic Mountains, high up near the head of the Beardmore Glacier. The rock unit is called the Maya Desert Formation, and the fossils pulled from it, the leaves and the little scraps of wood, became the basis for a species named in 1996. The name is Nothofagus beardmorensis, southern beech. It was described by Robert Hill, David Harwood, and Peter Webb, working from leaves and wood collected in that till. The species name honours the Beardmore, the great river of ice below the site, and what they were naming was not a tall tree. It was a dwarf, a deciduous beech that grew flat against the ground. Hold one of those fossil stems in your mind for a moment. The wood recovered from the deposit reaches a maximum thickness of only about half an inch, roughly the width of an ordinary pencil. That is the whole trunk. And when you set a hand lens over the cut end and begin to count, the rings do not stop where you expect. There are more than 60 of them, packed into that half inch, each one a thin, pale line marking another summer of growth. Sit with what that means. A plant no taller than the top of a boot, no thicker than a pencil, that had already been alive for more than 60 years. It grew that slowly because everything around it was working against it. Short summers, long dark, wind that never stopped combing the same direction across frozen soil. So the beech gave up on height entirely. It spread sideways, low and matted. The growth form botanists call krummholz, the same bent, ground-hugging shape you find at the tree line high in the Andes today. You count those rings one line at a time, and the counting itself tells a climate. Robert Hill and Jane Francis studied exactly that, the growth rings and the leaves together, and read from them the shape of the seasons. The rings imply at least 2 or 3 summer months warm enough for the beech to leaf out and grow, with mean temperatures around 39 to 41 degrees Fahrenheit. Cold, but not impossible. Warmer, in fact, than that same windswept bluff feels now. The plant was living at the very edge of where a tree can live at all, and it was holding on. But a leaf pressed in rock does not carry a date stamped on its back, and this is where the detective work turned from the hammer to the microscope, and where a single clue split the whole field in two. The clue was diatoms. Diatoms are microscopic algae that build glassy shells of silica, each one patterned like a piece of etched jewellery. Far too small to see without magnification, they live in the sea, and mixed into the same glacial till that held the beech leaves, scientists found marine diatoms, ocean microfossils stranded high in a mountain range, thousands of feet above any coastline. Some of those diatom species are known only from young rock, from the Pliocene. Their presence set a ceiling on the age of the deposit. The till and the beech inside it could be no older than roughly 4.1 to 3.1 million years. Read that carefully because the wording matters. No older than. It is a limit, not a fixed birthday. And a limit is exactly the kind of clue that honest people can read two opposite ways. One camp took the diatoms at face value. If Pliocene marine diatoms are sitting in the till, the reasoning went, then the sea must have reached inland not long before the ice carried this debris up into the mountains. That would mean the Great East Antarctic ice sheet was not the ancient frozen constant everyone assumed. It would mean the ice had shrunk dramatically, opening seaways across the continent's interior, perhaps as recently as 3 million years ago, and then surged back. In this reading, the little beech is genuinely young. It is a true late survivor, a forest clinging on into the Pliocene, while much of the planet was already recognisably modern. Peter Webb and David Harwood, two of the names on that species description, argued this dynamic view. The other camp looked at the same diatoms and saw a trap. The East Antarctic ice sheet they held has been cold and stable for at least 15 million years, far too long for any Pliocene sea to have washed through the mountains. So how did marine diatoms end up in the till? Blown there, they answered. Wind. Fierce polar wind can lift dry diatoms from exposed sediments and carry them for great distances, sifting them down into deposits far from any ocean. If that's what happened, the diatoms date the wind, not the rock, and the beech could be far older than it looks. George Denton, David Marchant and David Sugden built this stabilist case. Two groups of careful scientists, one deposit, one set of tiny glass shells, and a gap of many millions of years between their conclusions, all hinging on whether a diatom was carried in by the sea or on the breeze. That disagreement, known as the Sirius debate, ran on for 3 decades, and it has never been tidily settled. It is worth pausing here, because it would be easy to want a single clean answer, and the rock has not offered one. What the fossils prove beyond doubt is that a forest of dwarf beech once grew at this spot, a few 100 miles from the South Pole. What they do not prove cleanly is precisely when, and behind that one argument lies a whole culture of patient collecting, the kind of work that rarely makes it into the telling, because the beech at Oliver Bluffs did not arrive out of nowhere. It arrived as the youngest chapter of a long tradition of picking Antarctic plants out of stone, one specimen at a time. Turn for a moment to the other end of the continent, to Seymour Island off the tip of the Antarctic Peninsula, known also by its Argentine name, Isla Marambio. For decades, paleobotanists have worked the fossil-bearing beds there, and the numbers are their own kind of monument. More than 1,600 fossil leaves lifted from a single set of Eocene hillsides. Not 1,600 in an afternoon. 1,600 across many seasons of stooping, splitting, sorting and cataloguing, gathered into named assemblages that read almost like place names of their own. The Women Flora, the Cuculea beds, and others besides. Jane Francis, Imogen Poole, and their collaborators are among the researchers behind that long effort. Their method is the same patient craft that surfaced the little beech. You split rock. You expose a leaf compression the size of a coin, and then you compare, holding the shape of that ancient leaf against the leaves of the living relatives, the beeches and the podocarps that still grow in the cool, wet forests of southern Chile, of New Zealand, of Tasmania. The teeth along a leaf margin, the way a blade tapers, the density of veins, all of it can be read as a rough thermometer, a way to estimate how warm and how wet a vanished forest once was. That is the wider craft the Beard Morensis discovery belongs to. It is not a single lucky find. It is a discipline built on returning again and again to cold rock with a hammer and a lens, trusting that the continent's lost forests are still written in fragments if you are willing to read them slowly enough. The Seymour Island leaves told of a lush Eocene rainforest near the pole. The Oliver Bluffs beech told of that same forest world reduced, at the last, to ankle-high scrub. Same method, opposite ends of a long decline. So when you hold the image of that half-inch stem with its 60 rings, hold the uncertainty beside it. The most cited estimate places this beech in the Pliocene, somewhere near 3 to 4 million years ago, which would make it the youngest confirmed forest the continent ever grew. But the stabilists would push it deeper into the past, and even the researchers who accept a young age admit the debate over the diatoms remains open. Some argue the true end of Antarctic vegetation came earlier, with the mid-Miocene tundra that vanished around 14 million years ago, and that the Sirius beech is either a genuine last survivor or an older deposit reworked and carried into younger ground. The literature has not closed the case. Working scientists are still turning it over, still splitting the same kind of rock, still counting the same thin rings. What no one disputes is the plant itself. It was real. It was small and slow and tough beyond reckoning, a beech that lived 6 decades to reach the width of a pencil, in a place where the sun vanished for months and the wind never rested. Come down close now, to a single plant no bigger than the span of your 2 open hands. It grows at Oliver Bluffs, in the Dominion Range, high in the Transantarctic Mountains, a few hundred miles from the pole. Its branches do not climb. They spread sideways across the frozen soil, low and matted, pressed flat the way a palm lies against a cold floor. This is Nothofagus beardmorensis, a dwarf southern beech. For the length of 1 Pliocene polar year, you can stay beside it and simply watch. The year begins in a long twilight. For months the plant has held still under darkness, its bare twigs stiff, its buds sealed and small. Then the sun edges back above the horizon, and it does not rise the way you know rising. It slides along the rim of the world, low and sideways, tracing a slow circle that never quite lets go of the sky. Day does not end here in summer. The light only leans, brightening and dimming as the sun swings around, never setting, never truly gone. Shadows turn like the hand of a clock laid flat on the ground. The warmth, when it comes, is modest. Scientists reading the fossil wood and leaves estimate that this place held 2 or 3 months a year above freezing, with mean temperatures around 39 to 41 degrees Fahrenheit. That is cold by the measure of a forest. It is barely a spring morning to you. But to a plant that has waited out the dark, it is everything. The soil softens at the surface, meltwater beads in the grit between the sprawling stems, and the beech begins to work. Understand what the light means to this small life. In most high-latitude plants you might know, growth is held back by cold or by thirst. Here, the limit is different. Here the limiter is the sun itself, present or absent, and little else. So when the sun circles without setting, the plant does not pace itself against a night that never comes. It runs. Every leaf it can unfold, it unfolds. Every hour of that endless leaning daylight it gathers. The buds break. Small, tough, deciduous leaves push out along the prostrate branches, tooth-edged and low, angled to catch light that arrives from every side of the horizon in turn. Inside the woody stem, a thin layer of living cells begins to divide. This is where the year is written. Through the warm weeks, the plant lays down new wood quickly, and because it is racing the light rather than rationing against drought, the cells it makes are wide and thin-walled and pale. Early wood, the paleobotanists call it, the loose, generous wood of a growing season in full swing. Under a hand lens, millions of years later, that band shows up as a broad, pale ring, soft-looking, almost open. It is the fingerprint of a plant photosynthesizing around the clock, taking in light that circles and never rests. You could hold your breath through this whole summer and barely see the plant move. Growth at this scale is patient past the edge of watching. A season's work might add a sliver of wood no wider than a thread. The leaves do their quiet chemistry. The stems thicken by a fraction you would need instruments to measure. There is no rush that you can see, only the steady, invisible accumulation of a plant taking what the brief warmth offers and asking for nothing more. The air itself is part of this. The atmosphere of the Pliocene here would have felt raw and clean, thin-scented, carrying the mineral smell of cold, wet ground and low vegetation, rather than the heavy green of a warm forest. That is atmosphere, not record, an inference drawn from what the climate proxies suggest, not a scent anyone measured. But it helps to imagine standing in it. The wind moves low and constant across the mat of branches. That wind is why the plant lies flat. Decades of it, season after season, have trained every stem sideways so that the beech grows as a spreading cushion rather than a tree, its whole body ducking beneath the moving air. Then the light begins to change. It is not sudden. The sun's slow circle starts to sink, its lowest pass is dipping below the horizon, and for the first time in months there is a true dimming, a real dusk that deepens each day. The leaning day gives way to a leaning night. The plant reads this in the failing light and starts to close down. Growth slows. The dividing cells at the edge of the wood make fewer new cells, and the cells they do make come out smaller, tighter, their walls thicker against the cold to come. Only a thin, dark line of this denser wood forms, barely there, almost nothing. That is the whole of the year's late growth. Where a temperate tree would build a broad band of dense summer wood, this beech makes almost none. The fossils show it plainly, wide pale early wood and only the faintest dark edge, a ring that is nearly all beginning and hardly any end. It is the signature of a plant whose year is not divided into warm and cool so much as into lit and unlit, a life governed by the sun's presence rather than its heat. The leaves let go. Being deciduous, the plant drops them before the dark closes fully, pulling back what it can, sealing its buds, shedding the tissue it cannot afford to keep alive through the coming months. The branches go bare again, and then the sun makes its final low circle and slips beneath the rim of the world, and it does not come back. Now the long dark settles in, months of it, unbroken, the sky wheeling through a night that holds for a season. The temperature falls far below anything the summer offered. The meltwater freezes hard in the soil. The plant does not grow, does not photosynthesize, does not stir. It simply endures, dormant and flattened, its living wood holding one more finished ring inside it. Around it the frozen ground gives back no warmth. There is only the cold, the wind, and the small dark shape of the beech waiting, as it has waited before, for a sun that is months from returning. And here is the thing to hold, in that dark beside that plant. This is not a young shrub. When geologists later split the Pliocene till and drew out a stem of this beech, they found it barely over half an inch across at its very thickest, about 1.3 centimetres, roughly the width of a pencil. Inside that pencil-thin stem they counted the rings, more than 60 of them. More than 60 of these polar years, each one a full turn of endless light and total dark, packed into a stem you could close your fingers around without effort. Let that scale settle on you slowly. This plant is older than a human life. 6 decades of summers it has met and shut down from, 6 decades of leaves unfolded and dropped, and in all that time it has grown no thicker than something you might tuck behind your ear, and no taller than the top of your boot. A whole human lifetime of patience, and the reward is a woody cushion you could cover with a coat. It is not stunted by accident. It is exactly as large as this place allows, and no larger, and it has spent a lifetime becoming that small. Think of what those 60 rings actually are. Each pale band is a season the sun came back and the plant reached for it. Each thin, dark line is the moment the light failed and the plant closed itself against the coming dark. 60 times the world tilted its face toward this corner of Antarctica, and 60 times it turned away, and the beech kept the tally in its wood, one thread of growth at a time. No calendar was needed. The plant was the calendar, writing the years into itself in a language of wide and narrow, light and dark. Stay a moment longer in that final winter with it. The plant cannot know it is among the last of its kind on this whole continent, cannot know that the forests which once stood tall across Antarctica have thinned to this, a scatter of ankle-high beech scrub clinging to thawed patches of mountain soil. It only knows the rhythm it has always known. The dark will hold, and then the sun will lean back over the horizon and begin its slow circle again, and the plant will unfold what leaves it can and lay down one more pale ring. That is its entire world repeated, until it is not repeated any more. Somewhere in that string of 60-odd years, the pattern broke for good. The summers that let it grow grew shorter, or colder, or simply stopped coming warm enough to matter. The ground stayed frozen through seasons that once softened. The last leaves the plant unfolded were the last it would ever make. And in time the advancing ice took the whole low cushion of it, crushed it, carried it, and locked its pencil-thin stem and its 60 rings inside frozen till, where it would wait, unread, for millions of years. Exactly when that ending came is still argued by the scientists who count those rings today. Whatever the true date, the ice eventually closed over all of it, and the continent went white from shore to shore. Whatever the true date, the ice eventually closed over all of it, and the continent went white from shore to shore. Whatever the true date, the ice eventually closed over all of it, and the continent went white from shore to shore. It did not happen in a single winter. The cooling came in steps, each one a little colder than the last, each one holding its ground. Through the middle of the Miocene, roughly 14 million years ago, the air over the interior crossed a line it would not cross back. The mid-Miocene climatic optimum had come and gone. For a while, around 17 to nearly 15 million years ago, the world ran 3 to 4 degrees Fahrenheit warmer than today, and the East Antarctic ice sheet drew back into the Wilkes Land Basin, letting green ground breathe again. That was the last exhale. After it, the ice returned and did not leave. You can picture the lockdown as a slow closing of a lid. The margins had carried ice for millions of years already. Now the interior froze hard, and the summers that once thawed a few inches of soil stopped coming warm enough to matter. The stepped cooling that ended the Fries Hills tundra was the hinge. Before it, moss and shallow lakes and small insects. After it, a fully polar interior, sealed and still. The forests were already long gone by then. What died in that final step was the tundra that had replaced them. Stay with that place for a moment, because it holds the whole reversal in one valley. The McMurdo Dry Valleys sit today among the driest and coldest unpolluted places anywhere on Earth. Bare rock, frozen gravel, wind that carries no moisture. By most estimates, significant liquid water has not touched much of that ground, for something on the order of millions of years. NASA has walked its instruments across those valleys as a rough physical stand-in for Mars, and yet the same ground, in the mid-Miocene, held moss-fringed lakes. The Fries Hills sit about 2,000 feet above Taylor Valley, and their old lake beds still carry diatoms, ostracods, pollen, and the delicate parts of insects locked in gritty till. A landscape like southern Greenland became a landscape like another planet. The change did not reverse. That is the quiet weight of it. If you were somehow set down in that Miocene valley before the last cold step, you would not find a forest. You would find low ground cover, sparse and tough, shallow water catching a sun that never climbed high. No tall trees, no canopy, just the memory of forest, thinned down to moss, and a few hardy survivors, waiting out a summer that grew shorter every few thousand years. The ice was already most of the world. This was the fringe, the last unfrozen hem of a freezing continent. Then even the hem went white. Now let me say the one thing worth saying to you plainly, wherever you are drifting tonight, before we follow the ice to its rest. If these slow walks through deep time settle your mind, follow or subscribe wherever you're listening, on Spotify, on YouTube, or in your podcast app of choice. That is all. We can go back down into the cold. Here is what the trees still tell, even now, even buried. Antarctic fossil wood carries growth rings, and those rings are not only a record of years, they are a record of light. At these latitudes, the trees lived under months of unbroken summer day and months of true winter dark. So the wood shows wide, pale early wood bands and almost no dark late wood at the edge of each ring. That pattern means growth was driven by light, more than by temperature or water, a fingerprint you do not find in modern temperate forests. Under a hand lens, a paleobotanist can read that rhythm directly, one thin line at a time. Some of that wood is silicified now, turned to stone, yet it still shows bark texture and ring structure under the fingers. A log that fell into a Miocene lake bed can hold its grain across 40 million years. You could run a thumb across it and feel the summers. And the trees keep the scientists arguing, which is its own kind of aliveness. The age of the youngest beech material, the dwarf Nothofagus of the Sirius Group, has been debated for 3 decades. One camp reads the East Antarctic ice sheet as cold and stable for at least 15 million years, and treats the Pliocene-looking marine diatoms in the till as dust blown in from elsewhere. Another camp reads those same diatoms as in-place proof that the ice collapsed and reformed as recently as about 3 million years ago. Both camps are working paleontologists. Neither has been declared the winner. The last forest is a moving target still being placed on the timeline by people alive today. A study in 2025 pushed southern beech forest in West Antarctica into the early Miocene, later than some older reconstructions allowed. Each new core, each new leaf nudges the edge of the map. That is not a flaw in the science. That is the science still breathing. So when you ask when Antarctica's last forest truly died, the honest answer is that the question is open. Maybe the mid-Miocene tundra extinction, 14 million years ago, was the real end, and the Pliocene beech twigs are a survival, or a reworked ghost. Maybe a stand of ankle-high beech really did hold on until 3 or 4 million years back, a few hundred miles from the South Pole, growing so slowly that a stem no thicker than a pencil counted more than 60 rings inside it. A tree older than a human lifetime, shorter than a boot. Take one slow breath and hold that image, because it is the smallest forest the world has ever kept. Now let the view begin to lift. Rise a little above the valley, and the moss beds shrink to a smudge on the gravel. Rise further, and the Transantarctic Mountains become a dark seam stitched across white. The old lake beds, the silicified logs, the buried leaf compressions, all of it slides under a sheet of ice that in places runs more than a mile deep. From up here the continent is a single pale dome, turning slowly under the long polar light, saying almost nothing. But it is not empty of memory. Under that ice the wood is still there. The rings are still counted in the grain, the light of vanished summers still recorded cell by cell. The beech twigs are still crushed into the till exactly where the glacier left them. Nothing up here has forgotten. It has only gone quiet and cold and patient the way stone is patient. Let the whiteness widen until the coastline itself becomes a thin, bright rim against the dark ocean. The circling current still turning, still holding the continent inside its own long refrigerator. The forests are 100 million years behind us now, from the Cretaceous poles through the Eocene rainforest to this final huddle of dwarf beech. They did not vanish in a night. They thinned and dwarfed and lay down flat against the wind, and at the very end they did not so much fall as fade away beneath the ice. Let your own thoughts settle the same way, slowly, without struggle. The whole slow reversal is finished, and there is nothing left for you to hold up tonight. The continent turns below you, white from shore to shore, keeping its buried forests safe in the cold and the dark, exactly as it has for millions of years, exactly as it will for millions more. You do not need to carry any of it. You only needed to see it once, and now you have. Let the light grow soft. Let the cold stay far below. The last forest is sleeping under the ice, and it sleeps well. Sleep well tonight, traveller. Good night.